So we're going to extract some assets if we can, and we're going to have to find out how to do that exactly. It's been a while, so I have to remind myself how to do this stuff again, especially for the Z80. Let's see. Let's also look at our sim file. Right, so the approach here will be the main menu. I think the image in the main menu, that would be easiest. So let's look at C000 to see whether we can see something pop up there. Because that's like the standard scratch pad in RAM, I guess. Right, so that does change. If I pause here, now we can determine anything from this, of course, but I do assume that this is the representation of the image, or the screen at least. Right, I did make some headway in figuring this out, but it's been a couple of months, so I don't know exactly how I did it. There is a call right in the BIOS that transfers memory to the video chip, but of course I completely forgot where VDP routines. Yeah, so inhibits, displays the screen, write data. So I don't think it's this one though. I don't know. That's in the register. Writes data to the VRAM. The LDIR also applies, I think, because that's a block transfer, right? So maybe we can see if we can find a, well, it's going to be at 5C, right? So if we go look in the assembly, I don't think that's going to be in there, is it? No, that's not going to be this, right? No. Well, I mean, let's see if we can trigger anything here. Okay, so it's not triggering now, of course, because we are not, reloading the screen, of course. So I'm going to have to continue. Now it's loading the demo, so it's going to load several things into the video RAM. So let's let it load. Okay, and now I'm going to re-enable. Okay, it's going to do that constantly, I guess. Okay, that sucks. So I can't put a condition on this, I assume, because that would always trigger, right? I can't do a conditional here. I could put a write on C000 though. That might be a thing to try. So if we put a watch point, okay, maybe do it with the button. We don't need this, but we do need. Why does it not show my button? Because it's too small. Okay, that's fine. So add watch points right on C00. Let's continue now. And I go to the main menu, and now we break. I don't know if this is already the main window though, the main intro screen. Apparently not, because I can continue. Yeah, so it was this last one then. So I think I clicked 3 or 4 times. So let's do that again. Oh, well, no, I needed to let it go. Okay, reset. Okay, so now it's the, well, after resetting it, of course, has to render the main menu as well. So I don't know if it's this call, 6CD7. So what are we looking at here? Putting A into what DE points, the DE points to C0, and we're incrementing DE, so we're looping over like an entire thing here. So instead of doing this watch point, let's continue and see what fills up here. Okay, so it's clearing it out. Oh, and it is putting stuff in there. Okay. Now, question is, if we mess with this, then we might see something on the screen, right? So maybe it's good to look at the end of this function. So this is the loop, right? DJ and Z loops through all the pixels, I guess. So you will see probably the C register decrement, I think, or the B one. Was it the B one? Yeah, it's B1, 654321. Okay, so let's see if we can break here. Okay, so the question is, so we return here, but I don't see a syscall to the BIOS to actually put that into the memory though. So I'm not sure if that is actually the main screen. I'm gonna let it run and see if it breaks again, which it does. Oh, right, this seems to be, yeah, this is another run length encoding because it added like 5 C2s. Okay, so I think we're decoding the main image here in the main menu. So yeah, 1F and then 5, 4, 3 hexes. Yes. Okay, so this is still in the decoding routine, and I guess if we escape this routine, then we're putting it on the screen. So we see a return here. Okay, so I'm assuming that this is now our entire screen. So where do we end up when we go here? Okay, so this is this call. It's not putting anything on the screen though. So we are loading C000 into HL again. So we're going to do something with this information, and it is 800 hex tall or long, which is good. So now the question is, if we mess with this stuff, do we alter the screen information? So I'm going to put some C2s here. Oops. And see if we can see something visually different. I didn't write down my, okay, so it's this one, the function we were in, and that's a 6B6D. Okay. No, okay. So that was too early. We did not, so it's with all the 20s we have to do, okay. Okay. Yeah, this is, I think this is the, because I think 20 is black, and it also has the names here, Kamura. Yeah. So the Nakamura, okay, it's going off screen, but it says Nakamura here. Yeah, for sure. Maybe I can put my scale slightly lower. Oh no, that's the font size. Where was the font size again? Yeah. And of course that doesn't fit in the window. Okay, 32, that should still be visible. Of course it doesn't update. No, it doesn't. So let's restart. And of course it doesn't listen to that either. Oh, okay. I'm not sure if 32 is too small to see on the stream, but we'll go for it for now. So back to C000. Okay, so we need this here, right? So it does have the F Nakamura and Okayama and Suji here. So this is definitely the decoded main screen, right? Maybe I can put a conditional breakpoint on C000 when it becomes 20. Okay, that's a tickle expression. I don't know how to do that because I don't know tickle. I mean, I don't assume it's as simple as this. That does trigger. The question is, does it trigger now? Which it doesn't, of course. So I don't know how that works, but that's fine. Actually, it's going to be 20, right? Although it says 0 now. Oh yeah, no, it's writing, right. It's writing something in there, right, because it's loading the demo. Okay, I just have to wait until it's 20. So it's 0 now. Okay, so I'm assuming this is it, because it's starting at 20 now. So we're at 6D39 now. That's the exact same location, I think, which would be the algorithm that decodes the data, right? So I'm going to disable this one, and I'm going to break on the loop here to see if we are back into the run length encoding stuff. Yeah, so yeah. So it's doing a couple 20s here. I'm assuming it's going to be 20 hex times. So it's 32 times. Yeah. So that the B register is decrementing because of the D, J, and Z call here. So if we look here, then we're going to add like 1D hex amount of 20s in this area, right? That's exactly what we do. So this is for sure the decoding algorithm for the assets inside the game. I'm assuming, because the algorithm works the same way as the level data. It is a run length encoding for sure. Just not sure how it's stored inside the game itself. So all we have to do now is, because now we're in the right area, right? We have our 20s here. We just need to know where we are. I don't think we have a call stack here, right? So let's just break until the end of this function and then see where we end up when we return. Oh, that was a conditional return, crap. Oh, and this is the jump to 5C. Excellent. Right, so it jumps to 5C to put it on the screen. So I should have paused here. Oh, but then we don't know. Okay, we'll have to look at the stack because to find where we were called, right? Because this jump doesn't give us any information other than where we're going to. Let's see. So I'm going to do the same thing now. Yeah, so our 20s are loaded. This looks different though. Is this correct? Yeah, it says HAL 1985, but this is incomplete because, oh no, it's doing it in multiple goes, I think. Like it does the segment at the top and then at the bottom. So this is the top part of the screen with the image. So, I mean, now we can mess with the image, right? So 20 hex would be the black background. So if I put some 20s in here, we should see some black line where there isn't supposed to be one. So if I continue now, yeah, so these are our 20s, right? So we did mess with that piece of data. We're not breaking, so we're not breaking on the second right, it seems, which is fine. Okay, so I'm breaking again, but now I hope the stack is still intact, which it should be, right? Yeah, if we look at the stack, okay, my screen isn't complete, it looks like. So B3D0 appears to be where we're coming from. I'm going to open a dump. So I have a thing here to dump the entire disassembly, and I guess I can open, yeah, this makes it a little bit easier to search. So we're coming from B3D0. Right, and that calls 6D44, which is indeed this little function. 6D44 calls this one. Oh, I think I might have skipped a function here. Well, this is the function that actually loads the data, but the call is to 6D44, which actually just puts it on the screen. Oh, and this calls 6D1A, which is here. Okay, that's like a function that covers this decoding. Okay, so this might be the decoding algorithm. 6D1A called from here, right, and then it puts it on the screen. And then 6D44 is called here from this line. Hi Kim, we're extracting assets from the ROM, the Eggerland ROM. See if we can extract all the images and stuff, if that would be possible. It's been a while, so I'm not sure again, or still how it exactly works, but we'll do our best here. So I have to get back in the groove here. So 6D44 loads C000, presuming it's already filled up. I guess not. But I think the call to 6D1A is actually decoding that stuff, because the first thing this does, thanks. The first thing that this does is overwrite or load HL, right? 6D1A. Yeah, loads whatever is in HL. So I'm assuming that's going to be the encoded data, like the run length encoded data, which is then processed Yeah, so we're loading the first byte, we're increasing, we're loading the second byte. Yeah, and we're doing stuff with that. And it's already returning here though. Right, if it's non-zero, it jumps to 62A. Okay, so sure. I think that's just a null check. If it's non-zero, yeah, that does make sense. Like if the image is null for some reason, I don't know why that would be the case, then it jumps to the routine that decodes it. And then now over here we do have our ands. We're doing a bit check. Okay, we're rotating. Yeah, this is the decoding algorithm. Right, so what would be interesting to know is to log what HL points to at this location, because that's going to be the encoded data. Right? And of course, we already know this because we can just read this, of course. This is being set just before we call this function, and that happens to be B3F0. And I'm assuming that the first byte or the second byte might be the length, because we need the length to know how much data to decode, of course. So B3F0, which is a little bit higher up here. B3F0. So we're definitely in the ROM now because the RAM starts at C000. So B3F0, apparently this data over here, I don't think I can multi-select, this data here appears to be the top part of the main intro screen, the main menu screen. And the question is, this call should be in the code multiple times, right? So let me make a new file for notes. So our interesting one is here, and this call should be multiple times, and it is not. That's very interesting. That's strange, because I would have assumed that this routine was being used multiple times. Of course, there might be direct calls to 6D1A here. So maybe if we call, yeah, okay, we do see multiple calls to 6D1A. And this is also referencing stuff near here. Question is, why is that one different, right? So 6D1A, so the only difference between a call like this, well, no, it also calls 6D1A though. So we're putting something in C000. Oh, and then B31C is called as well. Oh, yeah, okay, that's right over here. So this is a little function that's being called. Okay, wait. Right, because over here we are putting it on the screen, right? The jump to 5C is is this one, load or LDIR VM, which block transfers it to the VRAM. Okay, sure. Right, so this does the same thing as this one over here. BC, okay, so this is a shorter piece of memory, D8. So we can experiment by removing this call and see what it omits. How could this difference be that this one is run length encoded and this one isn't? So wait, let's see. Look, so 61A is being called. That would be the decoding algorithm. Okay, sure. So this area at B585, that's encoded. That's run length encoded and is decoded in this call. And then we're calling this one to put it on the screen. Okay. And DE is a destination, not because it's called DE, but it's a DE register containing the destination for the elder function here. So we're putting B585 at C000, render it to the screen, and then we're putting the destination to 2000. I don't know why we're doing that. And we're also putting that on the screen then. Which one is here? So HL is the start address of memory, and DE is V. Oh yeah, we're putting it in a different location in VRAM. Okay, sure. Okay. So we're decoding this to C000, and then we're putting C00. So the start of memory in HL is C000, is being put at 2000 in. Okay, oh yeah, right. Yes, that does make sense, I think. Okay, we're going to start knopping out stuff so we can see what is what here. Okay, I'm going to make a copy of the ROM. So we have our ROMs in we're in the straight ROM to Eggerland hack, and then we're going to do a X patch, and we're going to open the hacked file. Okay, so I have the hacked ROM here, and now we have to look up which bytes to edit. So we're first gonna knock out the big one, the main one. Oh, we do have calls to 61A. So wait, let's look again. So 61A is the straight decode, but we were looking at B3CD, this one, 6D44, which doesn't occur anywhere else other than itself, of course. So let's start with this one. So we are looking for these bytes here, right? Let's see if we can find this. 21F0B3 CD446D. Yeah, that should be unique. Okay. And then we're knopping out the CD call. And we're saving. Now we're going to load the hacked. Oh, it's already loading the hacked ROM. Okay, I shouldn't have done that. And I'm going to disable my breakpoints. And see what is missing now. Yeah, it's the top part. So it's the graphical part of the menu that's now missing here. That does make sense, I guess. Let's see. Okay, can I undo this? Yes, I can. And now we'll knob out. So B3C1 is this one here, right? Let's not do that by. Okay, so it's loading at 2000, 2800, and 3000 and running through. So it's doing 3 sections. I don't know why it's doing that, because the data doesn't change, right? So this is a decoding function. Wait, oh, we have two calls here, 5.6 as well. That's also a BIOS call. 5.6 is, oh, fill VRAM with value. Okay, sure. So we're filling with black. Okay. So this is fill the screen with black. And then we're putting the menu on top. CD, okay, that's after that one. That's a bit weird, but I mean, I guess we figured out that this function here is the decoding function though, which starts at 61B, I think it was, right? Where are we? Yeah, this is our loop. Right, so we start, yeah, we jumped here to 64.4 and we're calling 61A, and that's the start of the decoding function here. So we're pushing the first 2 bytes on the stack here, which we're popping when we exit the function, okay? And then we're loading the value, we're ending C, which contains the first byte, comparing with B. If it's non-zero, we're exiting to 6040. Okay, so that's the entire function then, I guess. Yeah, okay. And then we're doing 63.7, that's here. Question is, how do we exit this function here? Okay, there's a return here though. Okay, I'm gonna look at this in the text file 61A. Okay, so our function runs from here to here, because this call at 64.4 is being called higher up, right? So I think this is our decoding function. Okay, HL contains the data to the encoded or the encoded data, which of course I can't see anymore. So yeah, this of course is being called often. We were here at was it this one? No, not this one. Crap, I lost my... Okay, no problem. I'll put this one back and we'll load the main menu. Okay, so we're not broken. Oh, we'll have to restore the ROM, of course. because I removed that call, of course, so it wouldn't be able to break on that. Right, so now it breaks, and our, okay, B3D0 is where we're coming from. So B, right, okay, I did have that here about, yeah, so this is the call to our decoding function, and the data comes from B3F0, which was, of course, here, still here. So C0, let's get the calculator with us here. So C0 is 192. That's a nice round number. That makes sense. When it comes to 11, right? So 192 over 11, I think, is a round number. It's not. Okay, it's half the screen though. Oh no, 11 doesn't make sense. It's not the game board, of course. But 192 does seem to be round enough when it comes to the amount of tiles horizontally. I don't know how many tiles there are horizontally. Can we see that? Yeah, this is empty now, so it's black, but that's fine. So we have 31 columns. Well, 32, I guess, because it starts at 0. Yeah, so if you do 192 over 32, that's a round number, I think. Yeah, 6. So we're doing 6 rows of 32. And how many rows do we have? We start at 0 and we go to 20, so 24 rows. Okay, that could make sense. So fine, we load the first byte and we load the second byte. Also, we do know how much data is being transferred, of course, because, so we're loading the pointer to the data, we're calling 6D44, which is the only call in the assembly that does that. So that means that in 6D44, which comes after this, we know the length because, yeah, so we're loading C000, calling the decoding function, and then we're copying 300 hex bytes. Oh, right, but that's decoded, of course. That's the yeah, of course. I can't confuse those. The C0 refers to the run length encoded bytes, which is of course way shorter than the 768 bytes. Yeah, this calculation doesn't make sense. So we have 768, which is also a round number when it comes to 32, right? No, it's not. Oh, I'm in hex. 768 over 32. Yeah, that's 24. And we have 24 rows, meaning that's an entire screen. So yeah, this is an entire screen. So the question is, these two C0s, whether it's indeed 192 bytes that's in here. That would be a coincidence, though, that it's like a round number. But fine, let's read some more. So we're loading the two first bytes and pushing it on the stack. Then we're loading the next byte. So we're loading C0 and C0 here. And then DF. So we're handing DF with the first byte, DF and C0. So let's look what DF looks like. So we have 4 bits at the bottom, 1 bit missing. And C0 is, of course, only the 2 top bits. Not sure why we're doing that. And we're comparing it with B. And then we're doing a relative jump if it's non-zero to 6D40, which is all the way at the bottom here. We're loading 1 into B. Oh, right, that's... And then we're jumping back. I think I recognize why this is 6D37. It's right over here. and then we're doing this routine, all right? But B is 1, so this loop only, this is a little loop, and this only gets executed once because B is 1 here, okay. So I think in run-length encoding, this is the case when we only have to repeat this byte one time. Right, so what do we do then? So we are jumping here, writing out. Okay, so we're loading the next byte. We're writing it into where DB points to, which is the C000 scratch pad in RAM, and we're increasing that pointer. And so we're doing this one time for now. And then we're increasing our byte in this one here. The thing I'm interested in right now is our exit condition, right? Because we have to reach this return here. That will be determined on the length of this thing. So I'm trying to figure out how long this piece of data is, because I don't know how long it's going to go on for. But if that's the case, then we can extract this data and then write some code and try to do our decoding ourselves. But fine. So we're looping one time here, increasing AH, HL, and we're popping our stack again. That makes sense to not have to reload these two first bytes. And we're jumping to 61E, which is again, okay. So we're pushing again, which also makes sense, I guess. Okay, and then we're loading the next byte, which then would be 20. We're ending it with C. So that's the only curious thing about this. So these two first bytes contain some information when it comes to the repetition count in the run length encoding, and that's not super clear yet. So let's assume now that we're not jumping here, because that's what you just did, right, with the one repetition. We're increasing our pointer to the next one, but I'm assuming that we just do that because we don't need that anymore. Oh, and oh, right. And if it's 0, so it ends with a 0. That's interesting. So if this fails, this AND fails, we don't make this jump. We're increasing the byte, and we're comparing it with itself. Well, in what is in the accumulator, right? And if it is 0, we do return from the function. So does that mean that it ends with 0? I'm going to add 192 to this, so B3F0. That would be B4B0, which would be here. And this does not end with 0, so it's not that. So the comparison here is with the A register, right? And we're loading the current byte into A, and then the next byte is compared to the current byte, right? That's a bit weird, and that's also not the case over here. So we have C3 and 1/8. So assuming it's not 0, we jump over the return, of course. And then we're loading C into A, C being our first byte here, C0. CPL, I don't know what CPL is. It's going to be a comparison, I think. So CPL is the contents of A are inverted. Okay, sure, we're inverting A, which would be C0 at this point. We're inverting C0, so C0, oops, is of course 192, becomes the inverse is 1248, 1632. Okay, minus the top bits, the top 2 bits. Okay. Oh, we're going back here. That's interesting. And we're ANDing it with, so we're ANDing it with the previous byte and then incrementing again. And then we're extracting, I assume, a certain bit. Bit 0C, test bit 0 of C. Okay. And if that's 0, we go to, we do not do a rotate to the right. Okay. We're adding 3. I'm gonna have to write this in C though. So I'm not sure about the condition, the exit condition yet. So we're rotating based on this bit 0 or not. We're adding 3 to A. Add is just add, right? That would surprise me if that's anything else. So add immediate, no, that's just add. So what was it called? Add A. It's an immediate that's being added. Do we not have like we have register additions, but we don't have immediate additions, it seems, which is fine, I guess, because I'm assuming it's just adding 3. That would be weird if it was different. Then we're moving A to B. We're loading the next byte or the current byte again, because we did go to the next byte again into A. Oh, and okay, so now we're loading A into a DE point. So this is actually writing it to C000, our RAM scratchpad. So this writes out a byte, and then we're increasing and looping, because this is the end of our loop CD. So we're doing this with whatever is in B. So this is the count. Okay. And we're adding 3. Okay. So the count, so this DJ and Z instruction looks at the B register to see how many times it has to loop, which we load here, coming from the accumulator, which we've added 3 to. Based on bit 0, we either rotated it right or not. Okay, and then C is loaded into A. So it comes from there, which is then inverted. Why so complex? Why so complex? What's interesting though is that we seem to, so if we do this loop here, so this little loop is being done n times, then we go to the next pointer, but we're popping BC, and BC is always the first 2 bytes, I assume, because we're pushing this, so we're pushing this here, right, at 61E, so we're popping it and we're immediately jumping and we're pushing it again. So what I want to inspect is the stack at this point in time, whether it's the first 2 bytes or whether I'm misinterpreting how this works. Because I'm assuming I don't see this stack value change though. So let's try that. So we're assuming it's going to be C0, C0 for the BC here, right? And so that's at 6D1A. So that's the start of our function here. I guess we're too late in this iteration. Maybe not. I don't know. That's a bit, yeah, because we have multiple ones here. That's going to be tough. Actually, we need to break when HL is pointing to B3F0. Okay. So no, not you. Okay, not you either. Okay, I'm going to go back to the menu, and now it has, so B3F0 has to appear in HL here. So it's not this one. Yeah, it's this one. Now HL is B3F0, so now we're pointing to these guys here. And we're broken here at 6D1A. So we're loading C0 into CMB. So BC becomes OC, OC. If we step over these, yeah. Okay, or C0, C0. Did I miss? Yeah, C0, C0. Right. So that makes sense, and we're pushing that on the stack. So if we look at the stack here, the top right, this is going to become C0, C0. Yes. And then we're loading what HL is pointing to. So HL is now pointing to the third byte, right? Yeah, so this is this one, B3F2, because we read in the first two already. So that's going to be DF. That's loaded into the accumulator. That becomes DF here. Yes. And then we're ending it with C being the first, well, one of the two. So DF and, okay, let's do that just to make sure we follow here. Where's my calculator? So we have DF and C0. DF and C0 is C0. That makes sense because that's the two top bits, and DF is right. So it extracts, okay, it extracts the two, oh right, it extracts the two top bits. So that makes sense, I think. So C0 is just the two top bits, right? So this might be a run length encoding algorithm where the, so within the byte, we're storing the amount of times it has to be repeated and the value. That's what they did for the level data and stuff. And this might be a dynamic thing where they store how many bits represent the amount of repetitions instead of hard coding this with ands. So it could be, so I think they're optimizing here. That could be the case. So the C0 here would imply take the top two bits for the length. So we can prove this, right, if we keep reading. So yeah, right, and now so we read DF, and we're extracting now the two top bits because we're ending with C, which would result in C0. Right. Yeah, that makes sense because DF had its two top bits set. So that would be 1 and 2, which is 3, right? Okay, so that becomes C0, right? And then we're comparing it with P. Oh, that's with the other byte. And if it is the same, which it is, we don't jump. Meaning we do our extraction here. Okay, so because this jump at 6D40, if we remember, this is just setting the repetition to 1. Oops. So this is not a 1 repetition thing. So I wonder where we're going to get the repetition count from then. Right, so if this byte and it with the first byte equals the other byte, I assume, then we decode a byte. Okay, let's continue. So we're increasing HL now, pointing at the third byte, even though we haven't done anything yet with DF itself. So we're pointing at B3 at this one here. Oh, okay. Because the 20 is the one we have to write, though, at C0. So we're comparing C0 now with 20, right? Because we're comparing what HL points to, which is the fourth byte, which is 20 hex, with what the accumulator contains, which is C0. Okay. And that matches. Why does that match? C0 and 20. So C0 are just the two top bits, and 20 is like the 4, 5, 6th bit. Does this give me more information to know what exactly this comparison does? So compare with, what was it? What HL points to? Well, I mean, that's of course clear. I mean, this instruction, oh yeah, it does. So subtracts what HL points to from A and affects the flags according to the result. A is not modified. Okay, so we're subtracting 20 hex from C0, okay. Which is A0, so the 0 flag would not be set. Right, that's correct, right? It subtracts 20 from C0 and affects the flags. I don't think that would affect any flags, right? Because we're doing 192 minus 32. That doesn't trigger any overflow or anything. And it does check the 0 flag. Okay. And that it is non-zero, so we do make the jump here, meaning we don't exit a function. Okay, sure. So maybe there's like a terminator byte at the end where that is the case. So what would that be though? Could it be this one here, this C0? Well, there's one here too, and here. Yeah, because HL has to point to C0 for this to stop, right? So would that mean that it runs from here? Well, no, because we have a C0 here. Maybe we can figure out what that is. Okay, never mind. So we're skipping our exit. That makes sense too, because we just started. And then we're loading C, which is one of the two first bytes here, into the accumulator and inverting it. So we're loading it, that becomes, so A is now C0, and we're inverting this. That becomes 3F. So if we look, C0 are the top 2 bits. Oh yeah, the reason why we're inverting this is also makes sense now. So we're flipping the 2 top bits to 0 and all the other ones to 1, which becomes 3F, right? So the reason why that makes sense is if we have a dynamic assignment of the separation within the byte, meaning which part contains the repetition count and which part contains the count, that means that if we deduce by this C0 that the 2 top bits contain the repetition count, we have to invert that to get the bottom amount of bits, right? Yeah, so that inversion does make sense. Okay, and now here we are going back. So we were at 20, but we're going back to DF, and that makes sense because we haven't done anything with the bottom 6 bits of this DF yet. 20 is going to be the value though, so so we're okay. Let's just continue. So we're decrementing HL and we're loading. Oh no, we're ANDing. Okay, so our inverted, right? So now we're extracting the bottom 6 bits of this byte, of the DF byte. Remind me why I. So we did check the 4th byte already, but okay, fine. So now we're extracting from DF the bottom 6 bits. So if you look at DF and we remove the top 2 bits, we end up with 1F, which would be appearing in our accumulator now. Yes, 1F. That makes sense. And we're going back to our 20 here. 1F is how much? 31. Could that be the repetition count then? Right, so maybe it's not a separation of repetition count and value, but more like the exit condition and the value. Okay, so we are pointing at DF still 0, 1, 2, and now we're increasing back to 20. Okay. Right, B3, F3, that's this one. So now we're pointing at the value we're going to repeat now. And now we're testing bit 0 in C. So again, these first 2 bytes, I mean, bit 0 is not going to be set, right? So that's going to be 0, I think. Yeah, because OC or C0 is just the 2 top bits, right? So the bit 0 is definitely not set. So we're skipping this rotate right of 1F. 1F was that extracted value from DF here, right? The bottom 6 bits of DF. Okay. So we're not rotating right, so we're jumping to this one here. Okay. And now we're adding 3. Okay. So 1F was 31, right? So we're adding 3, becomes 34, of course, or 22 hex. All right, that becomes 22. We're loading that into B. So we're removing one of our first bytes here. Okay. So, right, 22. Okay, that's going to be the repetition count, which we already seen because B is related to this DJNZ, which is the little loop that loops B amount of times, right? So whatever is in B is decremented and the loop is returned or continued. Okay, so that's definitely the repetition count, and that came from the bottom 6 bits of this byte plus 3. Okay. Then we are loading our 20 hex into the accumulator. We're just going to, yeah, we're putting this, okay, and we're putting that at C00 and incrementing. Okay, that's our little loop. So if you go look at, so I have to remember B3F0 here. So I don't forget that. Okay, that's the data we are decoding. And then if you go look at C000, that was 1 0 too many. Right, so this contains previous garbage now, but now we're going to put 34 20s in there. So the value 20 was hard coded in there, right? Because we're loading this. Yeah, we're loading it once, and then the loop is just these 3 lines here. So yeah, we're loading this once in the accumulator, so that becomes 20, And now this is the little loop. These 3 lines here are the loop. We're doing this 22 hex times, so 34 times. And we're loading, yeah, we're loading this 34 times. So let's see. Yeah, so that's the 20s are indeed being loaded there. So that's 16. That's 32, 3, 4. Our B is now at 1, which will, so of course we have to point to the next DE byte. Okay, so decrement and jump, yeah, we don't do because B is now 0, right? And now we increment HL, so we go back to our encoded data. Right, so these 2 bytes contained the information, yeah, the repetition count and the value. So I'm assuming that 24D8 is the same then for the next set of bytes. 24D8. So 24, if you look at 24 hex, that does not have the 2 top bits set. Okay, so that's a 1 repetition then maybe. Well, I don't know. The 4 here, the bottom nibble, also has a byte set in the 4 position, so that would mean something too, right? So let's see. So we're increasing HL. We're popping BC, so that becomes C0 C0 again, which is good. Those are the 2 first bytes here, right? So we're popping those into BC, and we're doing a relative jump to 61E, which is all the way at the top again, where we are pushing it back onto the stack. So we popped it, and now we push it again. Okay. Again, doing the same, we're loading now 24 hex, but we'll see what the difference is with the 2 top bits not being set now, which is the difference with the first sequence, right? So we're loading 24 hex into the accumulator. That makes sense. We're ANDing it with C, which we popped, which is a C0, right? The 2 top bits, which would now be 0, right? That the accumulator is now 0 because the 2 top bits are not set in hex 24. And we're comparing it with B, so with the other byte here. That was a subtraction, right? Was that? Yeah, I think it was. So we're doing B minus A. Right, I have to look again because I forgot. So CPB is, subtract B from A and affect the flags. So A minus B, which is, oh, now we are going to overflow then. Okay. Okay. Yes. And now we end up in our thing here where we load the repetition count of 1. Okay. So we jump over here indeed, we load our repetition count of 1. And we're jumping to our assignment routine to C0. So we're doing, oh, would it be the 4 then? Okay, wait, that could be the case though, or 24 maybe. Yeah, it's gonna put 24 once in the C000 area. So we're loading 1, and we're jumping to our writing routine. We're loading HL into A, that becomes 24 again, yes. And we're writing that to C00 only once. So we are here now. We're loading that there, that becomes 24. We're increasing our pointer to this one, that's fine. We will not be looping because we're at 1. So decrement and jump if not 0. We're decrementing first, and we won't jump because it's 0. And we're going to the next byte. So if the top 2 bits are not set, then we repeat this once. The question remains, why do we need 2 bits for that, right? Why do we reserve the 2 top bits and not just the topmost bit if it's a Boolean? So I haven't seen anything being manipulated with those 2 top bits yet. That's a bit weird. Okay, let's go look back at the data at P3F0. So we processed DF and 20, those were combined. We processed 24, that was just a 1 repetition. Now D8, I can already see D8, the top bits are going to be set for this one. Yeah, so they are going to be set, so we're going to repeat this. I take off the 2 top bits, that's 24 times, plus 3 is 27 times, we add 25. Okay. 26 top 2 bits not set, 1 time repetition, and then we have the C0. That's going to be crucial here, because that's going to match exactly. I think that might stop it even. Well, we'll see. So let's process, where are we? D8 25. That's, like I said, it's going to be 27 repetitions of the value 25, I think. So we're pushing, wait, right, we're popping and we're jumping and we're pushing again, right? We're loading D8. D8 is ANDed with C, has C0 in the top, because the 2 top bits are set, it's compared. We're not exiting from the function. 64, no, we're not doing a 1 repetition, okay. We're increasing HL, we're going to look at the next byte. Right, so HL is pointing to F6, which is, so we are extracting, that's interesting though, we're extracting the bottom 6 bits of the value byte. Right, because the comparison, the CP instruction is done with what HL is pointing to, which is pointing to the value byte of 25 now. Oh, and that's the exit condition. Right, so the exit condition is if the bottom 6 bits are defined by C0, so the inverse of this byte, if that's 0, then we stop. Which would be the case for this one, maybe, we'll see. So okay, we haven't reached the exit condition yet, so this is definitely the exit condition for this function. Okay, so same routine, right? We're loading C into A, meaning C0. Okay, we're extracting the bottom 6 bits, which is 3F. We're decrementing HL. We're going back to our D8 byte here. And we're ANDing it with what? So we're ANDing the accumulator 3F, meaning we're extracting the bottom 6 bits of this D8, which is going to be 1, 8, right? Yeah, I think so. Yeah, 1, 8, and then we're adding 3. So we're increasing. So we're pointing to the value bit again, the value byte. We're, all right, that's like a curiosity here. We're rotating to the right if the bit 0 of C is set, but that's always going to be false because we are confronted with our C0s at the front here. So we're going to have to find an asset where that is different. Because I don't think we're going to do this rotate anytime soon in this decoding, in the decoding of this data, because it starts with C0, C0. Yeah, so we're jumping over this rotation. Okay, we're adding 3 for 27 repeats, which becomes 1B, right? Plus 3 is of course 1B. and then we're doing the loop. So I'm going to break here, right? So because I'm not going to wait for the 27 repetitions, right? So it's going to be this one. And if we look at C000, we're going to add the byte 25 hex 30 or 27 times. So from here, 27 times this byte, got 25. Okay, that's this. Okay. So that we figured out how that works. So that's one's done. Now 26 is going to be a 1 repetition of the byte 26. That's the little corner in the like you have the left corner and then like 27 or however many top lines, and then the corner at the end that we're seeing here. So yeah, we're increasing HL, we're popping, and then we're jumping to the push. Okay, now we're loading 26. We're ANDing, that's going to be 0 because the 2 top bits aren't set. Comparing it with B, right, which is the case. So we're doing a 1 repetition, right? B is loaded with 1. We're jumping to our write routine and we're writing the byte once, right? The 26 byte is written once to our C000 area. We do not loop again, increase HL. And now it's going to be interesting because this C0 is the same here. Okay, we're jumping to the push. We're loading C0 into AF. We're ANDing it with C, with our original C0, which is going to be 0, right? Or C0, of course. Yeah, we're ANDing. And we're comparing it with the other one. I think this is the end now, though, because this is going to be... So we're subtracting C0 from C0, which is 0 itself. Yeah. Oh, there's an extra condition here. Wait, oh no, the 6D40 was the one condition, right? Oh, no. Okay, I'm too quick here. Yeah, we were testing whether the top 2 bits were set, and they are, right? Okay, this could be a coincidence. So we're increasing and we're checking. So we're increasing to 20 hex. Okay, this might just be a coincidence then. Okay, so we're comparing with 20 hex with C0, but 20 hex doesn't have those set, right? Yeah, it doesn't have the 2 top bits set. So we're not exiting here because of the C0. Let me think here. So we're subtracting 20 hex from C0, which is not going to cross the 0 boundary. So we're not exiting. So the C0 is then just... Oh, but yeah, we're going to extract the bottom 6 bits of C0, which is going to be 0, right? How is that going to work? Okay, so we're not exiting the function. We're loading C into A, C being one of our first C0s. That's fine. Inverting it to get the bottom 6 bits. We're decrementing HL, so we're pointing at C0 again, and we're ANDing. That's going to be 0, because now we're ANDing C0 with 3F. C0 has only the 2 top bits set, and 3F has the bottom 6 ones set. And if we AND that, we get 0. I'm assuming. Yes. We're increasing. Oh, and now, no, the rotation right is not going to happen. And we're adding 3. Okay, so okay, right. So the minimum is 3. It's as simple as that. That's why we're adding 3. We can't like exit out because our bottom 6 bits were 0. So we're not doing 0 repetitions, right? We're doing, because we add 3. We always have a minimum of 3. So we have to, if we have to repeat something 3 times, we do that C for that byte would be C0. Right. So I think we figured out how we are decoding the bytes here. Now the question is, I want to see the exit condition, right? So okay, let's continue this one till the end. So we're doing this 3 times. Okay, decrement, 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 that's it. And now we're jumping back to the next one. What I want to know is how I return here, right? So this jumps here over the thing. So this comparison, yeah. So if we break here, we know where we stop in this thing here. So let me continue this whilst removing this one. Okay. So now we're at the exit position. We know what HL points to, right? So HL points to B505. That's farther than I expected. B505 is this one. So that's the last byte. Oh, it ends with C0, C0. Is that relevant? That could be relevant though. So so what did we do? We loaded C0 into the accumulator here. We're adding it with C. C contained C0. That was one of the 2 first bytes. Okay. We're comparing it with B. That result would be 0. So we're doing the 1 repetition. Is the last byte a C0? That would surprise me though. I don't know where it ends though. No, it's not. It's going to be this 20 here, I assume. Yeah, so it definitely wasn't outputting. Wait, let me think. It's subtracting and comparing with B. I don't know what that result would have been. We're increasing and comparing with what HL points to. Yeah, I think that's the end marker. Simple as that. Well, at least we know the length of the data though. So let me extract that one. I'm going to make a new file here, and I'm going to put that in a CPP file, so we can write our little test routine. And now I'm going to go to the hex editor. I'm going to extract this data. I hope I can, yeah, I can multi-select. I'm gonna find CC. Oops. Did I make a typo? C0, C0, DF20, 24, D8, 25, 26, C0, 20. Why is this not found? Okay, stupid. Didn't wrap. So we start here and we end at the C0, C0, right? At B500 something. That's going to be here. That's going to be the data, I think. Yeah, C820. Yeah. I don't know how this is going to show up. Okay, fantastic. Right, okay, you can see the text here. That also, so these are the tiles, right? The tile IDs, I assume. and the tile IDs are mapped to the letters too. So HAL 1985 does show up here. So yeah, okay. I could have seen that, but sure. It's so all these guys are one repetitions, right? That would also make sense. But of course, this garbage doesn't paste here. How are we gonna do that? I think maybe the other hex editor does it better. Well, we'll see. I guess we can find this one too, or use this one, I mean. Why can't you find this? Of course you can. Yes, until 500. It was this, right? 38, 35C8, 20C0, C0, 74FEY. Is that number different? Oh, that would have. Oh, because it's not 16 wide. Okay, sure. So B500 would become 7500. Yeah, it's this one here. Okay, can I copy these bytes better? Of course I can't. Okay, let's just use hexdump then. Not the best solution, but I don't know what the exact thing was that I needed to use. I mean, this is going to copy too much, I think, but yeah, that doesn't really matter. Can we search in this too? We have to stop here. Right, we have to put OX in front of it too. I could do a stud array. Might change that later instead of a simple byte array. What is that? C standard int I have to include. I'm just going to compile this manually. Okay. I mean, do we know how many bytes this is? Because then I can put it in a std array selection. 278 bytes. All right, so let's see if we can copy this routine. Well, is this right? Yeah, it's this one. Okay, so we need to have the two first bytes. Let's give them a name. Prefix 1. And prefix 2, so we don't have to do stack pushing and popping, of course, which we can't really do. All right, so we're pointing at the third byte, so we have to have a current byte, a current pointer. Which becomes 0, 1, 2, right? Yeah. That would point to the second byte here, or the third byte, I mean. We don't need this. We're loading this byte into the accumulator and we're adding it with C. So we only have to be careful here which is prefix 1 and prefix 2. So C is prefix 1. Okay, so we're ending with prefix 1. Okay, sure. So yeah, we're doing, let's name it A, right? Data current index. This is going to end up in a loop, of course, because we are looping back to this line. 6D1E is being, yeah, so this is the loop goes all the way here. So this is the body of a loop, right? So we're loading the nth bytes into the accumulator and we're adding it with C, C being the first prefix, or the prefix 1. A equals A and prefix 1. And we're comparing it with B. So comparison was a subtraction, right? If B minus A equals 0, oh yeah, that's the 1 routine. Else we calculate the 1 routine, and this is the exit condition. Okay, sure. And then we take the bottom. So this is the other length calculation all the way to here. Yeah, well, and then, yeah, and this is the little loop that assigns. Okay, so let's give us a buffer to write stuff into. Okay, this should fill it up, right? I think so. Or does it not? I can't remember with the array. Where's my... Doesn't complain, so I'm assuming it's correct. So we need a repetition count, and then I'm going to write this loop body here, right? So that's the loop body, and that's the value. Yeah, and then we have a pointer into, and we have an output position, okay. That's still going to be a data index, and then an output index is going to be 0, and then we have a repetition count, and then in the end we're going to do and then we're going to write into output at current output index equals value so we just have to assign these things, right? We have to assign our current value, our repetition count. Those are the two main ones we have to calculate. So if you go look back, so that's our little write out routine, and then so we had a condition here, 6040 being the repetition count of 1 based on the subtraction of B and A being 0, right? Or non-zero. If it's non-zero, then we jump. And what was it again? So we're ANDing with the 2 top bits and subtracting that from the second write, okay, from prefix 2. So if the bytes, the current bytes ANDed with the first prefix, oh, we already did that, I assume. Yeah, that's this one, right? Yeah, C is prefix 1, but that's in the condition actually. Do we still need this because we're loading this? Yeah. I think we don't need this as an actual value in a variable, I mean. So we're loading the byte into A and we're ANDing it with the prefix 1 and comparing it with prefix 2. Okay. And if that is non-zero, then we set the repetition count to 1. Okay, I have to see if I can remember this. So I think if it is simply if A and prefix 1 minus prefix 2 not equals 0, repetition count equals 1. Is that correct? So the current byte, meaning our df here, and with prefix 1 minus prefix 2. So our current byte ANDed with prefix 1 minus b. So that's the operation is correct. The order operation is correct, right? Let me see. We're comparing CPB, right? So b is so it's A minus B. Okay, so it's accumulator minus B, meaning yeah, it's this. Yeah. Minus B. If that is non-zero, then we put the repetition count on 1, and we actually write out the thing. So then the else is, I think the exit condition can be done before this test though. Wait, do we? I don't know. So we're increasing HL, and we're, no, because we are comparing. Yeah, we're comparing the next byte with a manipulated value though, because the accumulator at this point still contains the result of this, right? So A is not it said A is not affected, right? In the CPB, yeah, A is not modified, so that we can ignore. So this one, it's this, right? So this remains in the accumulator at this point where we are evaluating the exit condition, because we're comparing the next byte with the manipulated accumulator here, the manipulated first byte, or in other words, the bottom 6 or the top 2 bits, yeah, the top 2 bits of the first byte of the accumulator. Yeah, we're comparing it with prefix 2, and we're comparing it with the next byte then. Actually, I'm gonna do this twice though, because it doesn't really matter when it comes to efficiency. That doesn't really matter, right? So if we are subtracting current data index plus 1, so the next byte, if that is 0, so if it's non-zero, we move away, right? But if it's 0, we return. So now we have to break, but we don't have a loop yet, right? So we have to break from nothing here at this point in time, but this will become a loop, of course. Although, no, because we have to loop over all the data bytes, right? The repetition count is just how many times we have to repeat over the same byte in our run length encoding. So this break will work later on. And then this is the else condition, and it goes all the way to here, right? This one too. So we're loading C, being the prefix 1, into the accumulator and inverting it. That's not right. Or is that an XOR? So we have DF. If I XOR with 0, does that invert? No. If I XOR with 1, no. Is there a C function for that? No, I'm not sure actually. Oh yeah, tilde. Okay, sure. Right, I didn't know that by heart. Never mind. So then, yeah, we're doing. Okay, that's prefix 1. So we're this is our else here, right? So we're gonna say mask equals prefix 1. Does that work? So the inverted prefix 1, which becomes the bottom 6 bits in our thing here. And then we're going back to the... So we're decrementing HL here because we incremented it here, right? Yeah. So we don't have to worry about that. Yeah, that's the test end condition. But we don't have to worry about that. We're ANDing with... So that's the current byte. We're ANDing the accumulator, which we have here. Okay, so we're extracting the bottom. Okay. Actually, I mean, I can do just mask equals mask, and it doesn't really matter. prefix, no, the byte, right? Data current. I'm gonna, yeah, I have to clean this up though, because that's a bit convoluted. Okay, we're increasing to the next byte, that's fine. So that's our value byte then, I guess. Yeah, I think I'm going to have to do this at the end to skip the current and next byte, right? Because in this situation, we don't have to do that. We just have to do it once then. Right, because that's this increment here, all right? Where, yeah, well, yeah, I think that does make sense though. And then based on, so we haven't seen this yet. So based on the bottom bit of the prefix 1, we are rotating right. So our arrays rotate right of the accumulator, I guess. The contents of A are rotated right 1 bit position, contents of bit 0 are copied to the carry flag, and the previous contents of the carry flag are copied to bit 7. I want to assume that a standard C or C++ rotate right does the same. I think we have a thing for that. Or is it only shift right that we have? I don't know. Actually, I don't know. How to do, oh well. Circular rotation of a byte. Okay, that's left, but I guess we can do something similar. Okay, sure. But we don't have a thing for that. That sucks, but yeah, it doesn't really matter. Because we haven't encountered it in this data set anyway. Like, this data set doesn't have any conditions, as far as we've seen, of course, that triggers this. But considering it's checking bit 0 of C, C being prefix 1, that's always fixed, right? Because it's this one, and that's never going to change for this data. So I'm going to ignore this. Well, I'm gonna add it, but yeah. If it is 0, we skip this rotate, right? So actually, let's not this one, but let's do this here. So if prefix 1 and 1, I guess, yes, equals 0. Well, I guess we have to do something. Right, we have to rotate right if the bit 0 of prefix 1 is non-zero. Okay, and then we rotate right the accumulator containing currently prefix 1. Oh no, the inverted prefix 1, which is our mask. All right. Did we already do this inversion? Yeah, that's this, but we extracted the, wait, we extracted the data already. So we're loading C into A, which is prefix 1. We're inverting that. Oh, and we're adding it here, but we're testing prefix 1. And this rotation is applied on the ANDed. Okay, sure. So it's not that we have to look at prefix 1, it's mask. So we have to rotate mask right one time. Right, the calculated value here. But we haven't encountered that yet, so that's fine. Then we're adding 3, and that's our count, which is mask, right? Yes. So actually we're dealing with the repetition. So basically this means that the repetition count equals the data and prefix, and then we rotate the repetition count to the right. I think that's what that means, right? Prefix 1. Yeah, and then we're adding 3. Well, yeah, I have to do this first though. So the rotation has to happen before the addition of the 3. So then we do plus equals 3. And then we just need to know the value. So yeah, we're loading that into the B register. That's for the DJ and Z for the loop count, repetition count, and then we're loading the next byte into HL because we incremented here, right? And then we're looping out. Okay, so that's simply current value equals current data index. So data current index plus 1 plus 1. And then we're outputting repetition count amount, the current value, and that's just incremented by 1. Not sure if that's going to work. And then we have to loop though. Right, so our exit condition here can become a return, right? Well, let's see. So this can be a simple while loop. If this remains true, or well, the inverse, of course, then we have to keep doing this. So we simply have to reassign this at the end of this, right? Because that's this jump here, right? 61E. Yeah, we're loading. Yeah, that's the first thing we do. So actually, if we do this after this, we can put this in a while loop, right? So if we say while not equals 0, well, I need to run braces here, and then I put this here. I think that makes sense, right? So a and prefix 1 minus the next byte not equals 0. I don't know. This could contain a mistake and loop forever, right? Like, I don't know. So we'll try that. Just to make sure we're not seeing this. And we're going to output our data now. Right, so now we dump this out. I'm going going to do this very inefficiently, but that's fine. Output I. Oh, no, that's wrong. Not data length, right? We have to... Actually, I'm going to put all 1024 out. Yeah, let's just do that. Yeah, it's not that data length, of course. It's going to be the buffer length. And we do output I, and then if I larger than 0 and I modulo 16 equals 0, let's see, we have to specify our C++ version for standard format, which I don't remember how to do. I did compile something else in the same way. Yeah, that's this is the one. Let's see if we have mistakes. We don't have any mistakes. Okay, that actually looks good. Let me add some padding here. That's like this, all right. Yeah, because we have 20s. Okay, so now we have to compare it. Let me remove the OX so we can compare it with the output here. Let me put a clear in front so we can see just our thing here. Okay, this is our data. Oh, yeah, it's messing up with the thing. Why is this not... I always make this mistake. Why is this not working? Well, I mean, it doesn't really matter, right? Like this 20 should be on the next line, but fine, I guess. So let's see, let's compare. We'll go to C000, and it still contains the data we need. So we have 20s, we have 25s, then a bunch of 20s again. No, this is wrong, because there's way too many 20s here. Okay, we're definitely making a mistake here. But at least our initial 20s do work though, isn't that good? I guess we'll have to output some debug data to see what we're doing here. Although we are ending with a bunch of 20s too, so that's fine. So I don't know how big our length is here. Can we see? Yeah, we have, so let me fix this first. Okay, I'm just gonna put it at the end. We have 30 lines, 30 times 16, right? That's 480, that's half a screen, right? Yeah, I think that's half a screen. Yeah, but it's not correct though. Oh no, 480 decimal. Yeah, because times 2 is 960. Was it 960? Yeah, okay, we're making a mistake somewhere. No big deal. We'll just have to debug. Where can we go wrong? So let us dump the repetitions at least. So we have a repetition count, we have a value, the value would be in hex. Current value, yeah, we do have that value. Let's put an enter after that. Okay, yeah. Okay, so we have 34 repetitions of 20. That's what we saw, right? That's correct. Then we have a, right, what was the address? B3F0. Yes. So we have df20 implies 34 repetitions of 20. Then we have 1 repetition of 24. So the incorrect thing here is the 20. Right. I'm missing. And then we have d8 repetitions of 25, which is 27. That was correct too. But then, yeah, we're missing our changing of our thing here, of our value. So why are we not? Oh, okay. You have to assign it, of course. That would make sense. And that would be the current byte that we have to do here. That would make more sense. Yeah, okay, that looks way better. So now let's compare again. I don't think that will have fixed everything though. So we have a bunch of 20s and 25s. Then after the 25s, so we start with 24, 25. Right, so those are the corners, right, of the little thing at the top. So we have 24 and then a bunch of 25s and 26. So that makes sense, that's correct. And then we have a couple 20s again, 27, 20s again, 27, 06, 03, 4, 6. Okay, this does look to be pretty much correct though. Yes, it does look to be correct. Okay. That was easy. Yeah, this is exactly correct. Yeah, we have our 20, 29, 2 A's, 2A, 2B. Yeah, this is correct. We can keep a tally of the amount of bytes we've outputted. Actually, we do we know this? Yeah, this is going to be current output index. All right. Yeah. We do only, we don't have to do output length here. We can do this, all right? Yes. Because we know how many bytes we've written out into the data, of course. I don't think I'm off by 1. I'd have to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, I'm not off by 1. Right, so this is our decoded data, and now of course this data represents tile IDs, I assume, so we have to extract those as well, at least the pixel values of those things. Oops. So if you go look at the tile viewer, and for example, so 20 is going to be black, of course. Well, yeah, that's going to be 32. Of course, these pattern numbers here are decimal, right? So 20 hex is 32, of course, which is a black thing. Also, we're in the wrong palette here because the pattern table is for the game now. This is not going to be correct because we need the menu screen, right? So I'm going to continue. Yeah, that looks to be better. Although, yeah, that did change, I think. Yeah, because this wasn't here, right? Or maybe it was. Let me just continue. Okay, so let's pause. Yeah, am I crazy now? Was this different, or am I seeing things? So let's wait for the demo. Yeah, these change. So it's loading a different, yeah, of course. It's loading different pattern tables, like sprites for the game itself, of course. So I'm going to go back to the main menu. And we'll see that this top row changes. Right. Preparing for the display of the menu. Okay. Because these numbers wouldn't make sense if we look at tile IDs for whilst the game is running, then we wouldn't see the tiles for this intro logo, of course. Okay, no, I didn't want a demo. I forgot to pause the game. Okay, so 20 is black, of course. So 13, 11, wait, why is this different? Let's look at my output, because I think I'm in the wrong position here. Yeah, this is something else. Right, so this is the bottom, as you can see, right? This has the names of the people, the F. Nakamura and stuff. So it does this into, so the data for this that we just decoded is just the top half until HAL 1985. Yeah, which is still here, apparently. Okay, so this is shorter than, yeah, I mean, you can see that, right? So the top part runs all the way with the 20s at the bottom. These guys here probably like is part of this black line. So this part at the top is bigger than this part at the bottom. So that does make sense that this HAL stuff is left over. It just overrides the data. Doesn't really matter. So let's look at 24 and 25. So 24 is going to be this corner here. Then we have a bunch of 25s, and then we have 26, which is this one here at the top right. So 25 hex is, well, it's 2 16s plus 5 is 37. So if you look at pattern 37, what do we see? Right. So 25 is the top, that's indeed the top. So the thing that you see over here is indeed, so it's 36, 37, and 38, right? Those are indeed the three edge pieces for the thing, right? And then, like, it's pretty cool. What they did is they, like this lettering isn't here, right? So they just took the unique parts and put those in the sprite sheets. That's pretty cool. Yeah, so that's that one, and then 39 6 is that corner, right. That's pretty cool. But yeah, so like we can also look at this call, for example. That would be pattern 434. Wait, that's way too much. What? Why is it taking a thing that's so high? Because it's repeated here, right? But it's gonna be this one, which is 181. So we have to find a B5. Should be in here, unless that's a sprite. Is it? So is B5 in here? It is not. That's interesting. So it's only doing the main logo, the Eggerland Mystery thing, and not these guys here, which is fine, right? Like the yeah, it doesn't really matter, but the art. This piece of art only contains the brick Eggerland thing and the mystery text and HAL 1985. Yeah, because this lettering here is probably HAL 1985. So we're seeing 15 hex is 17. Oh, no, that's still the blue lettering. That's interesting. Is it this one then? Yeah, this one. Yeah, 41. Yeah, that's going to be lettering, I think, because that's just ASCII, I think. So that's 29. 29. Wait, what? That's an arrow. Wait, no. Of course, wrong. 41 is 65. 65 is, it's not ASCII, I think. It is. Yeah, it is. So 65 is capital A, which is, so this indeed says HAL Labs, copyright 1985. Okay. Right, so we have a decoding routine which is not complete yet because we are missing this rotation here, right? This one here, we're breaking on that now, or we're triggering an error on that now. But we have to encounter a piece of artwork that's in the code that we haven't, that has that condition correct, because it all depends on these on the two first bytes, right? B3F0 on C0 and C0, because it simply checks whether the first C0 has the first bit set, meaning it would be an odd number then, right? Yeah. Okay, so now let's see where we call this function, right? So it sucks that we can't deduce the length without running through the algorithm, right? That does suck. Now, instead of using this array here, I'm going to reference or load the entire ROM, and we're going to get the pointers to all the artwork offsets that we can find, and put those in the little code here, so we don't have to extract or export all this data manually. We'll just read them straight from the ROM. All we have to do is, like, we have to extract 4000 hex from this address, and then we have the ROM offset. Right. Okay, let's look at the code again. So the call is going to be at 61A. I assume that's going to be in the code quite a bit. Let's search for the entire thing. We have nine calls to this thing. That's low, I guess. Well, I mean, considering that this call wasn't in the assets either, that could mean that like it might make sense that it's not really, that there aren't more references to it. Because they can, like, if we look at the game, there aren't that many places where there is hard-coded assets, right? So I think in the password selection screen we have a couple. Why is it not? Oh, because I'm still breaking, of course. Right. So yeah, this might be a screen that changed, right? The player selection that changed. And then the password selection screen. Yeah, this one, the border then without the sprites, I assume, is also one with the little flowers and stuff. But and the construction mode. Yeah, the construction mode as well, because yeah, this is all sprites. I don't think this will be encoded in the ROM. Although I'm not sure, actually. This could be just printed text, and maybe this line, I'm not sure. I guess we'll just we can break on these things, right? We can just break on every call to this function and see whether we can figure out what it is. So if we, so we'll just clear, and add them one by one. And the reason I'm not breaking on, I mean, I could break on 6D1A, of course, too. I just wanted to see the individual positions because I'd have to look at the stack, of course, which I could do as well. That's true. But yeah, I mean, it doesn't really matter. I think this was our original one, maybe. So 3BE1. Yeah. B3E1 we have, B3AF. Okay, I think, and that's 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so I think we have them all. Okay, we break because of that's going to be the main menu, I assume. So B3AF, yeah, that's the one we already had, right? No, that's the one we already had. So B3, okay, so 64.7, yeah, that's the one we were looking at because that's the one that has, that's close to where we were, right? If we look back at our code here, yeah, so B3CD, right? What's B3CD again? That calls 64.4. Okay, that calls here. Okay, no, that calls here. Oh, well, sure, yeah. Okay, I was confused because I was thinking of this one, but this one doesn't call the decoding routine directly. It's this one, so 64.4. In this function, it calls the decoding routine, but that's the main menu. So okay, 64.7 is a main routine. That means I don't know what B3AF is, right? It did break on that already, but B3E1. So we can look at the lengths too, right? So we're writing at C000. We're decoding and we are writing for a length of E0. So what we can do here is, how can we knob that out? So we need to jump. I mean, I guess we can, guess we can reduce the length to 0, but it would just put garbage in place, right? That would be, I mean, we would notice that too, of course, but also the fact that it's writing this at position 1820 into VRAM, I'd have to look at that too, though, because that might affect things too. Okay, so let's go to the next one. I mean, surely it's going to be these two, right? That, I mean, why else? What else would there be? It does end up in the second one. So yeah, it's doing the top one again, I assume. Because now I pressed space bar, so we're transitioning to the player amount select and the game type select. So it's gonna have to repaint the top one and then a different bottom one, I think. Yeah. Oh, it didn't even touch that one, probably. Yeah, it just left that and just repainted the bottom part then. Okay. Sure. And then let's see if... So it's calling something immediate. That's also strange. Unless that's a clear screen. What do we have in HL 9097? Wait, I'm correct here though. Am I 61A is the yeah, that's the decoding function. So if you look at HL, we see what we're decoding, right? So 9097 there. I mean, what's strange though is this doesn't contain this two values of the same, like not like the C0 C0. So this might be interesting to look at as well. Well, I mean, we're going to look at them all, of course. Okay. Oh, I'm still in construction mode. Okay, so yeah, construction mode does contain something too. Okay, sure. So we're doing 2 for the main menu. I'm pressing spacebar for this one. And now I think in the password screen, we're going to break 2. It's playing the music now. Yes, and now we are painting the, so that's 2 for the main menu, 1 for construction mode, and now 1 for the password screen, 2 for the password screen. We're at 5. And we're painting it in game 2, so that's 6, 7, 8, and maybe we're missing 1, maybe for the bonus level, because that's different, right? Oh, we're still broken. Okay, no, that's 9. That's 9. Okay. Okay, so now we're going to transition here from hard-coded encoded data to referencing the ROM. And I do have a previous file I can look at because I already did that before. I guess I can open this project too, though. Eggerland levels. So I don't have to like figure that out again. Right, so we are going to specify the path of the ROM. It's F-stream, right? Yes. And then we're going to use seekg to go to our offsets, and then we just have to specify the path to the ROM, which is located here. Okay, so we have the file available. Now we just need a list of offsets so we can, and we're gonna switch that over to a different function. And we need a offset in ROM. And we're going to just dump that to out the standard out. I'm going to get some information though printed as well. And that's going to be offset in ROM. Data is unknown, but data will be read here too. So we're going to pass the if stream. and then we don't know how many bytes to read, so we're gonna do like 1024 or something. That should be long, that should be big enough, because we're always limited to the amount of data we can copy into VRAM, so it doesn't really matter. We'll just read in like 1024 bytes. So we will seek to the correct position. From the beginning, and then we will read out. Yeah, I read this into a thing, right? But we don't need this, we just need individual bytes. So I'm going to make an array for my data. Let's put that in a I think, am I using data length? No, right? And that's going to be data initialized to 0, and then we're going to read into. I don't think I have to. I might have to cast that. I think I can just read it into like this, right? Okay, it is complaining about that. Right, I do need to reinterpret cast, and I mean, it looks bad, but right, so I think we have our data here. Then we have to just copy some pointers over. So this was the link, the call to 61A. I think we started at B3F0, right? So let's take that to test with. Yeah, B3F0. I mean, I can pre-calculate the offsets, of course. So B3F0 minus 4000 hex, because the ROM is mapped into address 4000. So that becomes 73F0. And then we have actually, I will just put main underneath. That's easier. Okay, so let's see if we can still do this. Where's my window here? Yeah, that still works. So we have removed our thing here, right? So that does work. Of course, this belongs to this function now, right? So that's, we can't make that global anymore, because it has to reset for every thing. Okay, so we have our first that works. Now let's try our the second encounter we have here. Right, so that was this one. And that was the only one, right? So that was the only one. So we're not using 6D44 to call our decoding function anywhere else. So we should be able to find all these offsets like this one. Okay, let's see if it works, right? I'll remove the first one for now and see if this crashes or not. I don't know if that is correct, of course, so I actually have to test that then. So let's stop here at B3AF and see if we can trigger that and see if our output matches oh, well, it's this one, right? So it's this one. Now we have to go back to the main menu. It's weird that this control stop not always works, though I have to press that multiple times. So B3AF, okay. So we're decoding the address at B585. B585, okay. That's okay. That's C040. So it's already different in the sense that it doesn't start with C0. So I don't know if it's going to be correct. So we will look at C000, and it hasn't executed yet, right? So we're loading this. I mean, it's calling B3C1. Oh yeah, that's probably a paint function. B3C1 is here. Yeah, so we're loading C000 and we're jumping to 5C. Okay, so because we're doing this multiple times here, fine. B585, okay, and we're looking at C000, so this is the output, and we'll skip over this function now, the decoding function, and this output should match with what we have, and I don't think it does it? Well, we have F1s, a couple F6s, FEs, yeah, no, it does match. 11 E6s, F4s, F1, 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 yeah. Yeah, it stops with this F4 here. So now to figure out what exactly this is, then I'm going to mess with these values. So we can make a note here. So this one is main menu top part, and then we can, so we know what is what, right? So I'm going to mess with these values by putting garbage in there. And see what changes. Of course, nothing. That's weird. That's weird. So, why would it not show anything different though? Or is it already too late? No, it's not too late because the paint call hasn't happened yet. So it happens when we go back from the game. Come on. To the main menu. Unless, okay, so now I have to think, so we're loading from B585, we're decoding that, but we might be writing it in VRAM elsewhere. And the question is, because like different things might be encoded with the same algorithm, right? So it's not necessarily all screen information. Because if you look, B3C1 is right here. It loads C000 where we have our source information, and it's D8 amount of bytes, and DE wait, which one was the address in the offset in video memory? So we have 5C, right? We're using 5C. Yeah, we're using 5C to paint to transfer to VRAM. And DE contains the start in VRAM where we actually write this out, right? So at this point, DE is set at C000. and I don't know these by heart. There is a screen, I think, that shows my information. Yeah, these guys here, yeah, C000 is not in this list. That's a bit weird. So let's see if we can look at the VRAM. Right, so it is written to this position, but I don't know what that represents on screen, because like we don't have anything here. That's too far, right? 1B. Yeah, that's way too far, of course. Yeah, I don't know what is being written here. So, I mean, nothing changed either, though. So, right, we have our stuff here decoded. And we're going to write this here. Oh, no. It's not writing to C0. It's writing to 2000. Right, I didn't see that. Okay, it's writing to 2000. Okay, sure. It's writing it here. And is 2000 hex in our registers here? Ah, yeah, it's the color table. Right. So this isn't artwork. This is the color table, which is encoded in the exact same way, apparently. If these are colors, then we should recognize these values, though. Where's my output? That's weird, because those don't look like colors to me. But okay, let's do this to see if it does something special. So yeah, we're writing this at D2000, and so the jump to B3C1 happens now, and that just loads in the source pointer and the length and puts it on the screen, or writes it into VRAM. Right, so that's now here. So this is our color table now, right? So yeah, it's at 2000 here. I do have to look up what this exactly means. I mean, I'm assuming this is the color tables of the associated sprites. But I like... And there's no reference here of the 2000. And the tiles, neither here. Well, no, the tiles, there is a difference. Yeah. Okay. Okay, so did this change then? That would be interesting to know if that palette changes, because if the VDP palette can change like this. So we have a length of E8, was it right? Where are we? This call at position 2000, we're calling B3C1. The length was D8. 216. Yeah, I have to figure out what that means. Not sure about that, because we're going to need that color information too if we want to render our extracted assets, our extracted artwork. Then we have to have that color information as well, of course. Oh, and apparently we are writing the exact same data at 2800 as well. First, let me see if this color palette changes, though. I'm not sure about that. I don't know enough about the internal thing here. No, it doesn't change. So what is 2800? Okay, 2800 does not appear here. Unless it's this one, but we have to go back to the main menu for that. I don't see any reference to 2800 though. That's weird, but fine, I guess. So, and it's the exact same data, right? So we saved both the exact same data. Okay, I lost my thing here because we're not broken anymore, of course. But that's fine. So this appears to be color table data. So let's add that comment. Okay, and then the next one. Yeah, 61A. Are we starting at the top here? Okay, so 9097 minus 4000 is 50, of course, 5097. Let's see what that is. And here we have something that we're doing wrong. Very good. So we're at 9097. Where are we? 9097. That's here. Wow. Okay, let's see where that is. So we were here in this line at 6B88. Let's try to break on that breakpoint. I already forgot the number. 6B88. That's this one. Okay, it's password screen stuff. Do we see anything strange? We're also loading this at 2000, implying it's also color table information. Also, this was color table for main menu, right? For the main menu thing. Oh, or was it? I don't know. I don't know. I don't know if that was in that vicinity. We have a length of 800. That could be too long. I might not be reading into enough bytes. 800 hex is 20. Okay, that's 2048. That's probably why we're crashing. Maybe. So let's go a bit longer. Maybe that's the reason. I mean, we're reading 2 kilobytes here in one go. Yeah, that was the reason we're crashing here. Okay, so this is a lot. And this is the password screen, right? Okay, yeah, that's the reason why we're crashing, simply. Because those were just arbitrary selections of buffer lengths. So let's decode, let's look at it, see if it's the same. And let's execute the decoding. Okay, that looks good. So we're starting with a whole bunch of F1s. Let's get my output here. So yeah, a whole bunch of F1s, A6s, 71s. Yeah, that looks to be good. Okay. And this is the password screen, right? I assume. So we are right, although we're writing this to 2000 though. Well, I have to look at the main menu again to see what where we were writing this, because I forgot. So this one, 73F0, which is B3F0, okay. No, that's the data I need to, yeah, well, B3F0 I can look up, right? Yeah, so we are jumping, or we are loading this, decoding it, and we are, did we write it in 64.4? Yeah, we did. That's a length of 300, and we're writing it at 1800. Okay. That's the name table. Okay, so that's the name of the. Okay, so those are the IDs of the tiles, then I guess. But what's weird is we are writing like 2 kilobytes to the color table here. I think so, at least. This is, yeah, these are VDP registers, of course. Yeah, this has to be this 2000, right? Yeah. I mean, I guess it's password screen color table. We'll figure this out later too when we're actually decoding stuff. Okay, that's 6B88. Wait, we might pause here multiple times, and we don't. The next one. So we had 9097, and then we have 97D8 for a length of 780. No, for a length of 80 hex. 61A is the decoding routine. 6PBE. Okay, 6PBE. That's this one. We might have to go back. No, it's from the. Okay, it's from the. Actually, I should change OpenMSX so I can knob out a thing here immediately though. Because I want to remove this and see what doesn't get painted, right? So that's 97D8 minus 4000 is 57D8. This is going to be in game, I think. Aha, here we have the not supposed to happen one, so that's very interesting now. So this is going to be different, right? So if we let this execute, we're at C000. Where are we? Yeah, here. So now let's let this run. Let's let the game decode this. It didn't change anything. Oh, what's also interesting is, oh, we're doing weird stuff here though, because we're not loading. So our memory origin pointer is at C140, which is like here. So we're skipping, it's like here, we're skipping like this entire first batch for some reason. And we're calling 6B3A 2 times in a row. 6B3A. Okay, so 6B46 calls the transfer to VRAM. Okay, weird why that has to be in its own thing. And the length is 2 kilobytes. Okay. This is confusing. Why we're doing this twice? And DE, the target is 0. The target in VRAM is 0, unless we are like manipulating that though. Okay, so we're calling this, okay, so we're doing 3 times. Okay, yeah. We're doing this 3 times, right? So 6B3A, they all end up with a paint call and with a transfer to VRAM. And the first 2 exchange HL and DE. And then loading 800, like 2 kilobytes into DE. Oh, it's doing 3 chunks. Okay, so it's chunking 2 kilobytes at a time. Wait, 2 kilobytes. I'm saying that it's 800 is 2. Yeah, that's 2 kilobytes. So it's chunking that 3 times. Okay, and it's like progressing because it's adding 800 hex, so 2 kilobytes to what HL is pointing to. Okay, sure. So that's 3 times 2 kilobytes that's being copied. Question is, where are we? So I should stop here, right? Because that's those 3 calls. So I know exactly what is being what the target address is of all 3 calls, right? Because we can here see. So 5C, let's get the thing again. So 5C, these are the meanings of the registers, right? So we're copying from C140. Also, the reason why we are doing C140, because we're doing 2 kilobytes at a time, right? So we're not starting from C000. And this is the second iteration, right? So we already copied the first block, now the next block. So that will probably increase next time too. And we're targeting DE 780X. So do we stop again here? Yes. Now F80, and we're still at C140 though. That's so we're copying the same bytes like 3 times into VRAM. And now something different. Okay. Yeah, considering this is a generic transfer to VRAM from memory call, this is not just like the tile IDs, this is also the color tables and the name table. Yeah. So this is multiple types of information that we're copying, and apparently they are encoded in the same way with our little algorithm here. Okay, fine. Now, the interesting part would have been the errors we got, right? They're not supposed to happen errors here. So let's figure that out. So we are looking at, where was our source data again? At 578, that's 978, right? 978. Okay, so we're starting here with C140, and it, yeah, that the 40 wouldn't have the top 2 bits set, and I think that was being checked, was it not? I don't know. It's bits. It's the bit 1 has to be set. Yeah, it's C1. It's not C1. It's not C0. It's C1. So indeed, the bottom bit is set now, and that wasn't supposed to. Now we have to do the rotate. Right. I have to figure out how to do the rotate right in C++. We can do this with the bit manipulation though. That should be fine too. Yeah, because if we have to rotate, I mean, it's going to come down to this, right? Repetition count equals, what was it? To the right, meaning 1. I have to look again because I can't remember. Yeah, this is left. So what do we do for left? We have to move everything 1 to the left and C7 to the right. For right, we need to move everything right 1 bit and the bottom bit 7 to the left, right? That's just the inverse, I guess. Right, let's see. So to do right, we need everything right 1, and we need this 1 to the left 7, right? That makes sense, I guess, right? So does this work better? No, unless it's something else. Okay, we're in infinite looping, I guess. Okay, no big deal. We'll just debug a bit. That's probably wrong though. So repetition count. What is this? What is it? Okay, that's a size T. So let's make that. Okay, sure. Let's start with that to make sure we're not overflowing here. Yeah. Now let's see if our thing is correct here by comparing the outputs. I don't know where we are now, so we're gonna have to reset here. So 578, that's 978. Where are we in the code? That does 978. Oh, okay, that's just data. Okay, never mind. So 6BB8 is the breakpoint. No, not 6BB8. It's the call is 6BBE. Okay, we still have a breakpoint on that. Okay, good. So I don't remember where that was. Oh, that's right here. Wait, why are we? Oh, it was in game then. Okay. Okay, so let's look at what was the target. Was the target hard coded to C000? No, right? Yeah, the target, where do we write? We write here to DE. DE is being set, yeah, before this function. So that means that we're writing to C400 now, not C000 for some reason. Okay, let's decode. Okay, C400. Let's look at my output here. 81s, 8Bs, 81s, D1s, F1s, P1, B1. Yep. 91 VF. Yeah, I think that looks correct. F2s, F4s, and that's it, ending with 14. Yeah, that looks to be correct. Although we're not sure where we are writing this. Because we're right, yeah, I don't know where we are writing this. Also, the fact that we decoded this into C400 and then we're using C140 to put this into RAM, into VRAM, I mean. Or this is weird. I mean, the thing we can do is like mess with this data, but like I don't know if it's gonna crash if I put like a bunch of zeros in there. But I guess we'll figure it out. Okay, so it's breaking again here though. That's curious, and it's going to be the exact same data, right? So I'm gonna decode again. Yeah, that's so weird. Like I don't see anything change when it comes to colors or now. Of course, we may be like influencing the color table of things that are not on the screen, right? That's also possible. I don't see anything weird in the pattern table here. Nor anything in the sprite table. Okay. Fine. So this is something in game. I don't know exactly what it represents. Okay, let's look at the next one. 978. So we're looking for these calls. B212, which is 7212. Okay, something short. Let's see where it breaks. AE44. That's this one. And we will exit this. We're not breaking here. Maybe construction mode. Nope. Nothing here either. We do have a second password screen though. Yeah, we have a, I don't know if I have this as a save state. The password, the special word screen, right? Yeah, no, that's too late. I guess we need level 100. But I don't really want to play that one. Unless it's bonus 20. Yeah, bonus 20. That's the one after round 100, right? So I think we will be able to enter the password in this screen. So maybe we'll trigger now. I have to just wait a bit, 20 seconds. Unless I speed this up. C81D, I mean the 20 seconds are going to be up though, yeah, of course. But yeah. Okay, yes, yeah. So we're breaking now because the next screen is the special words entry screen. So let's compare, let's execute the decoding. Okay, where are we writing to DB61? What? That is weird, but does that match? Yeah, 24, 25s. Yes, it does. It stops at 59. Will be for 5. Yeah, 59. Okay. Are we missing the 3A here or not? That's the question. We might. What is the length? Oh, I didn't even see the ASCII representation. Yeah, it's the password thingy here. Yeah, password and special word. Push any key, colon. I'm looking for the BIOS call to paint this on the screen though. AC43. It's quite far away. Yeah, that's an L there. Okay, that's copying stuff. Sure. Weird, but it is password screen related though. So that's something we do know at least. Special word, I mean. Okay, let's mess with the values to see if we can, well, I mean, we know we can influence it, of course, because this is we can see it's password and special word, right? So yeah, it has to be. So I'm gonna remove some stuff, I guess. Yeah, it's the line, I assume, underneath password. Yes, that's the line underneath, the blue line that I removed. That's gonna contain the border, the password word. Then those are sprites, and a special word. Then, oh yeah, no, this is not the special word entry screen. This is the screen you get after finishing a bonus round. Right. So yeah, this is not special word related. This is yeah, this is after you finish a bonus, you get the password for the level, and you can order for the next 5 levels, and a special word if you were good enough, which I wasn't, because it doesn't really show. Okay, next one. So we have this one too, AE44. That was B212, okay. And then this one, BOB8. So we're here now, we're looking at BOB8. Minus 4000 hex is 70 B8. Oops, I didn't need to close that. Let's see what this outputs. Ooh. Very weird. No, not 70B8. We want BOB8, I guess. Okay. That's not dynamic, right? That was a hard-coded. Yeah. And we're outputting that in C000. We're decoding it. Okay. First, let's see where this triggers, right? So we have AE6C, that's this one. Let's see where this one triggers. Oh, so this is a special, okay, sure. Because I was doing bonus around 20. That's fine. Maybe something in this one. Nope. Maybe in construction mode. Nope. Let's go through all the things though. No, nothing in construction mode. Not in the password screen. I am going to do the demo thing again, the bonus 20 thing again. And the timer was in C81D. And let's put that on 5 seconds, so we don't have to wait. And let's see if we break here. Yes, we do. Now the question is, why do we need a bunch of zeros, right? So we are writing those at C000. So let's look at that. So I'm going to do the decoding. And it is apparently a bunch of zeros. That is so weird. Because I don't see these being used. So let me look on the big thing. Right, so B212 was it? No, BOB8. Yeah, this one here. So we're loading the target is C000. We are decoding our thing here. We're loading C81B into A, decrementing it. Sure, increasing this 5 times. Also a weird number, I'm subtracting 5. That is so weird. And we're overwriting DE here because DE still contained our pointer thing to where we are decoding this value, right? Wait. Oh, did it go all the way here? Did I make a mistake here? Because this might be part of it though. Yeah, no. Because I see that DE here is C300, meaning that's in the routine, that's the thing that keeps track of how far it went, right? Because we are writing at DE and we're incrementing, right? So we can determine here what the end byte is here too. So I'm making a mistake here because I need way more than this. Yeah, okay. Yes, so it's doing the zeros, but then it stops. So we have 16, 32, 3, 4, 16, 32, 3, 4. Yeah, so the zeros are correct, but then the next 2 bytes are not. So for some reason I'm stopping here. So there is a bug in there for some reason. Because that is indeed the screen for the special word, I think. We were at the special word thing, right? Yeah. Or the password screen, I guess. Yeah. Okay, let's see. Yeah, so our algorithm is not working for this routine. So let's go look at the source data again. We are at, where are we? Not this one, is it? Yeah, it is BOB8. Yeah, BOB8. So E0, E0 are the 2 prefixes. Oh, so now, okay. The difference is that we now have 3 bits that are relevant at the top instead of 2 bits, which was C0. So now we're splitting this byte with 3 bits at the top and 5 bits at the bottom. Okay, that shouldn't make a huge difference though, but yeah. Yeah, so, okay. I mean, these zeros, those do worry me because how would they not error out, right? If we go look at the code. So we take in the first E0 is 0 and then I think this one triggers immediately when it encounters these zeros here. So we have FF for the first data byte, right? So FF and the top 3 bits are E0, okay, minus the next byte, which is 0. So we have FF minus 0, or no, E0 minus 0, which isn't 0, okay. So we continue. FF, and so that becomes E0 again, minus E0 is no, okay, this is 0, okay, so we're not in a single repetition count, okay, because the first 0 will work, right? Then we take the bottom 5 bits out of FF. Okay, so if we have FF and we drop the top 3 bits, we have 1F, which is 31, and that's what we're seeing in the output, right? Well, plus 3, of course, 31 plus 3, because we add 3. And do we do the rotation? No, because the bottom bit is not set in E0, so we're adding 3. Okay, so we're doing that. That is good. And then we move on to these 2 zeros here. Right, so now A is 0. And so 0 and E0 minus the next one. That is 0, so it quits. Right, so how does that work? Okay, I have to loop through the routine with this data. Yeah, we're already too late here, so we have to redo that. Let's play. I want to go back to bonus 20 starts. I can't remember the timer again. C81D. Okay, and then we go back to BOB8. Okay, and then we go into 61A. Okay, we start by reading E0 and E0. Good, we're loading the next byte, FF, we're adding it, we're taking the bottom or the top 3 bits, which is E0, comparing it with B. It's not a single repetition one, okay. We're increasing HL, which is the next byte, the 4th byte. We're comparing this with what HL is pointing to, and we do not return, okay. Then we're loading C, so E0 into A, inverting it. That's 1F indeed. We're going back to the previous byte. We're adding 1F and FF, which is 1F, of course. Increasing back to the next one, testing that bit. That's not going to be set, so we're jumping over the rotation, adding 3, so for a total of 22 hex, which is indeed 34, which is what we've seen. And we are outputting this at C000. All right, so yes, so let's do that. I'm going to break after the loop because I don't want to click 34 times. It's going to put 34 zeros in this area. Yes. Okay, and then we're popping, going to the next byte in the loop. Okay, now it becomes interesting because now we are handling these 2 bytes here. They're both 0. So we're loading 0, ANDing it with the first prefix, and that becomes 0, right? Yeah. Now we're comparing it with B, which is the second prefix. So we're doing yeah, 0 minus E0. Okay, so we are oh no, this is the check for the repetition count being 1, right? So we are jumping to 6D40. Oh right, okay, so it is. Oh okay, this is what goes wrong. Okay, because we are jumping to 6D40. 6D40 is the repetition count of 1. So that is the thing that is wrong is this. This one doesn't trigger for 0, 0. So we're doing A and prefix 1. A being, so they're both 0, right? So 0 and prefix 1 is 0 minus E0. So which of these guys is the wrong type? They're both unit 8s. As well as the accumulator. Yeah, this is an overflow or underflow thing that isn't triggering my the same flags in the CPU as the Z80 does, and that sucks. It might be the not equals though. I might have to do signs stuff and check whether it's greater or not, or equal to 0 maybe, or greater than 0. Yeah, so the CPB here is B minus A, right? And that is prefix 2 minus, oh, is it the other way around? Right, CPB equals, subtract B from A, so that's A minus B. And that means if the 0 flag is set by that, A minus B. So 0 minus E0. Okay, but it's the jump is made when it's non-zero. Why is it making a... Okay, so the relative jump is based on the flags, right? So show me the flags, because the 0 flag is going to be not set, right? Yeah, the 0 flag is not set. That's this whole 1 complement thing, or 2 complement that I don't really know by heart. So what are they trying to do though? If so we're loading the byte in the accumulator, and we're taking the bottom 5 bits, right? Because that's I think we're taking the bottom 5 bits. Wait, did we invert? No, we're taking the top 3 because we're not inverting yet. The inversion is here. So we're taking the top 3 bits. I mean, it's going to be 0 anyway, right? Because the input is 0. I think it comes down to, I'm gonna force this now. If we do a signed version of this, if this is, oh no, sorry, I'm wrong. No, not at this line. Okay, I want to do it's this line that matters. I think if this this subtraction, if we do this signed, if it's not equal to 0, I think if this is smaller or equal to 0, then it's 1. Not sure. No. If it's the inverse, then no, that's the same. Unless I do it with this one only. Okay, and then we do this one. Okay, that remains E0. And then we do the subtraction. What are we missing? Some brackets, I assume. Wait, why is this? Oh, it's FF. Okay, no. Right, no. The problem isn't the fact that our repetition count is wrong. It's our early exit here. Yeah, no. Because we're not. So I was thinking we're doing this with the 00, but no. This is the first byte, the first data byte, which is FF. This is correct. it's the fact that we don't progress here. So this is triggering. Right, I have to look at the exit condition. The exit condition is triggering. So where are we here? Oh, wait. Yeah, so this is my fault. I switched these around. So this does the... Yes, I see what's happening. So I switched these around, right? So the game checks the 1 condition, whether it's a repetition count of 1, before it checks the exit condition. And I did the other way around, and that's why it fails. Because this will jump to 6D40, meaning it will do a 1 repetition, and the consequence of that is, so it sets the repetition count to 1, and it jumps to 6D37, which outputs to the memory. And then it increases the HL pointer, and it jumps below the return condition. So yeah, it's the return condition that's messing me up here. And it's hard to do because this is a neat while loop, but if I have to, it's hard to switch these around. Yeah, that sucks. I think it was not equals 0, right? Yeah, if it's non-zero. Crap. How am I gonna fix that? Because that's not fun. Like, hello, Chubby Puppy Bear and K Martinez 915. Thank you for the follows. Let's see. I mean, I can do a while through, of course, and then have it break out like this. Of course, I mean, it's an else too, right? So I have to force this in here. Right, so that's our break, but this can't execute, so I have to do... And now nothing comes out, fine. Okay, sure. Wait, but no, if it's not set, of course. And if we do it as an if instead of a while condition, then we have to invert, of course. It's still not good because I don't think it's enough. At least we have more information now, though. Now the question is, do the other ones still work, right? Before we go further. No. Wait, why is it F3, F0 still works, but the other ones don't anymore? Crap. Oh, right. No. We have to... we have to ignore this exit condition if we have if the thing is set. Because yeah, that's what happens, because this takes precedence over, so it has to immediately do this and then go to the next one. Yeah, I think that's better. Nope. Yeah, I think we're breaking for all of these immediately, right? Well, no, I'm not outputting any routine, of course. That doesn't give me any information. So I mean, that does make sense, though. We only check the repetition count being set before our exit condition. So if it is the case, we set that it's true. So this can't happen. If it's not set, we calculate the extended repetition count and we output. Why is this not outputting though? For anything at all? Oh, wait, what? Okay, is there a different bug here where I can't do two at the same time? Am I not resetting something? Okay, I'm not resetting something. What am I not resetting? That's silly. Oh, right. I need to. Does this not work with? I mean, it is starting from the start, though. Is my seek wrong here? Data. Where is data? Okay, data is here. Wait, how does this work? Because my thing was working though. Like I could see when I did only the last one, it was working. But what am I doing wrong here? That file is not being closed. It's the seek operation should count. Okay, -1. That's not good. So that's the problem. It's not. Why can't I seek to two random locations one after the other? That's weird. Oh, that's a stream pulse. It can't do stream pulse, I guess. Can I pass this to a size T? Yeah, so, okay, we're seeking to FFFF, okay. What is this nonsense? Why can't I do random seeks? That doesn't make sense to me. Oh, does that not have random? I mean, I don't really care. This doesn't have to be efficient code, so let's just not be stupid here and just do this. And just open the file 10 times. Why are you shadows a parameter? Okay, sure. Let's open this file 10 times then. That's better, I guess. Okay, that's a stupid time waster. Okay. Okay, let's separate it a bit more. Okay, that seems to be correct. I still haven't fixed that stupid thing here. Like, why is that wrong? Like, I bigger than 0. I mean, that is correct though. You should have that. Now the first one is on the first line, I guess. Yep. I mean, that doesn't make sense, right? To make it 1. Nope. I don't know. So yeah, these look correct. Now they all seem to be working. And now the last one works too, right? 7OP8. Yeah. Okay, let's compare again with data in the memory. You can see here. Okay, I'm gonna let you run. But okay, can I jump out? Yes, I should be able to. Yes, okay. So this is our C000. Okay, so we have a bunch of zeros, then 24, 25, that's the border thingy, 27s, yeah, D0, D1, D45, okay, that seems to make sense, 5Bs, and we end with 72s and 73s, yes. Okay, we decoded that as well, so that's good. Now we were at AE6C. Yeah, this is password script, the same thing, right? But something else. This appears to be graphics data though, so this is mainly and this appears to be graphics data for the password script, so I don't know what the previous one was. Let's see that one again. Right, that was a short one. Not sure what it was again, but yeah. Okay, 1, 2, 3, 4, 5, 6. We have 9 of them, so let's look at the next one. We did BOB8, right? Yep. Next one is B27D minus 4000, 727D. Okay. Okay, short one that we have to check though, because I don't know if this is going to be correct. 727D, that's going to be at position AF0F. That's this one. Let's see if we can trigger this one. Okay, it doesn't trigger yet. Maybe in construction mode. Virtual keyboard was still on screen. Nope. Okay, I don't know where this one triggers though. What else could we have? Like, there's nothing here, right? There is a dialog for when it comes to the disk saving, perhaps. Like this one. Okay, now I crashed probably because I'm loading tape and there's no tape in there. Yeah. Yeah, we're not breaking here. I'm gonna wait for the demo. Where could this break? I don't know any other place that we have left where it could be like data like this being decoded, because we don't have like an end screen. Like if you finish round 105, you just go to round 1 or the main screen again, the main menu. Maybe type B does something different. Or maybe it is the password entry screen. Yeah, that could be it. So if you go to bonus 20, I've already forgot C8F1, nope. C81D. 4 seconds. So not this next screen with the password, but the screen after. This is a special word screen, and it's not this one either. Okay, so I don't know where this is. Let's see if we can find another then. So where were we at? B27D. So that was this one. And then the next one is at BOB8. We already had BOB8, right? At 70B8, I think. Yeah, this one we had. Then B585 we had. B5DF. Is 75DF. We don't have 75DF. Also a small one. B5DF, that's this one, B3E1. B3E1, that's the first one. Let's see if we can trigger that one. Yeah, okay, that's probably gonna be the bottom part of the thing, the level selection, or the game type selection. Let's go, so it's right into C000. Let's look at that. I will decode Okay, and it's for E0 bytes. E0 is 224. That seems low or high for this. Is this so? Oh yeah, that's 64. That's 128 and 64. Yeah, okay, that could be the case. What do we have? 20s, 11s. Okay, that's not good. We have 1, 2, 3, 4, 5, 6, 7, 8 20s, a 13, and then only 2 11s. And I have like a whole bunch more. Yeah, that is indeed the bottom part of the game type selection. But we are not decoding it correctly though. So up until here, 14, 20, then it corrects itself. And this is part of it, right? Yeah, which is not part of my thing here. I need to export the length as well, so I can see if it is correct. I think that could be -1 because we start at 0 and we increment over here, right? Yeah. So that's incremented, so it's -1, right? And I'm also going to put that in hex because in the assembly it's in hex. Yeah, df is not correct because we are copying E0, which is 1. Okay, that is okay. I mean, df plus 1 is E0, right? So should I not put wait, so we start at 0. Oh no, because the first byte it increments to 1. No, I shouldn't do -1. No. Because we start at 0, the first byte is 1, right? Okay, sure. Yeah, E0, so the length is correct because it says E0 here to copy. So we're definitely not including these guys here. So the 20s over here. Yeah, it stops here. So these asterisks are not part of it, which makes sense because there's nothing underneath. I think it's simply the text with the borders. But it is wrong, right? So 13, 11, 11. So the 11 is being repeated way too many times. And then for some reason it skips them too. Unless we're over, why would we be overwriting though? Because from the 14 onwards is correct, right? Yeah, how can that be wrong? That's so weird. Like if I put my 11s here to mimic what we have here, we will miss, like if I let it run, Yeah, that's definitely wrong. Well, I mean, that's also weird though, why there's a 1 there. I mean, that's super weird. I'm gonna have to do that again because that doesn't make sense. So yeah, let's break on that. Can I return here? And I cannot. Do I have a thing for the menu? I guess not. Why are we decoding this already? B5DF, so this is where we were, right? B3E1, yes. Why are we decoding B5DF or 75DF when we are loading the game? Wait a minute. Decode this? Because there is a border there too, though. Okay. That is super weird because now it has the names of the people in there. How is that possible? It's the same data. B5FD, that's 75DF. So B5DF and 75DF in ROM. Oh, and does this match then? Wait. Does it match now? 20s? Yeah, of course. So, of course. 11s, 14. Okay, how is this possible? So, my thing was correct, though. Now it is correct with all the 11s here. Oh, and the reason... Okay, sure. The reason why there was a 1 there is because in the top it says 1 player or 2 player. That's why there was a 1 there. I overwrote the text that says player by my 11s there. Yeah, of course. So this is correct. But how is it using the same thing for the next screen? That's super weird. Okay, so let's continue. Okay, so that's just the rectangle with the asterisks and the names, right? And then I'm going to the next screen and we break again. So the thing is hard-coded, right? It's hard-coded loading from B5DF. And if I decode it now, it has different text on it. How is that possible? So, of course, that makes sense, of course, that the thing is different here. So my 11s here are gone. Because now it says 0-1 player or 0-2 players or whatever. Like if you look at the screen now, yeah, it says 1 player or 2 player, right? So that's why there's no 11s here anymore. But how is it using the same decoded data unless the text isn't in there? Yeah, the text isn't in there. Yeah, so the text here, construction 4.3 for F, that's not going to be in. It is in there. So is it overwriting? I think it's because it's obviously it's the same rectangle, right? I think it's so the only weird thing is like they could be reusing the first rectangle, the complete rectangle with Japanese names in them, and then overwriting with type A, type B construction, the 1 player and the hard. But why does this also happen in the 61A function? That is pretty much impossible because the 6D1A function is simply the decoding algorithm. 6D, that's this function that we completely copied. This is impossible. How is that possible? That's so weird. Okay, we're gonna have to do this. We're gonna have to step through this though. Yeah, this is pretty much impossible though. How could this ever be? Especially because this is a hard-coded value. Like at this point in time. Wait. Okay, so let's try again. I'm going to go back to the first iteration. Okay, so now we decode, and purely the decoding does the names, right? Okay, so the names are in there. We haven't put it on the screen yet. That's this call to 5C. That's going to put it in the VRAM, right? So let's go there. Also, oh, does the data change? That could also be the case, of course. B5, well, no, B5DF is in the ROM, right? So we can't change that. So B5DF, okay. Yeah, that points to B5DF. That is our encoded data, our run length encoded data. And you can see that the type A and B stuff is right underneath that. Okay, so I'm gonna let it paint. Okay. And now I will do the same break in this one. So we're going to B5DF. Wait a minute. Oh, I see what's happening. This is, so HL is B631, which is literally the thing here, right? That is this one, which is pointing out to this one. We're being jumped here. We're not, yeah, we're not jumping. This wasn't executed. These two lines, or this line wasn't executed. We jumped through either this one or this one straight. So let's look at the stack. We're coming from B322. Yeah, it calls B362 and it loads B631 into, yeah, of course, now it makes sense. So B631 is another one then that so that's 7631, so we have to fix these. So this is, no, this is not correct. So this is game type, this is main menu. Yeah, and now we will have both. And one has the 11s, which is the straight line, and this one has the text in it. Yes, with player 1, player 2, or 1 player, 2 player. Yeah, these are both different. Okay. Okay, so we figured out those two as well. And I think that's about it though. Do I still have calls left? 9097 becomes 4097. We have 97D8s. We have, what is this? This doesn't have a an HL loaded into it immediately because we have a relative jump here, 63.7. So we are jumping here to 6D44. Oh, no, okay, that's the original one. Yeah, that's the P3F0. We have that one too. DB61, do we have? No, B212. We have BO-B8, we have. Yeah, B27D. We have B5, no, BO-B8, B585. B585 we have two. And B5DF we have as well. Okay, I think we're looping now. 9097. 9097 we have. I don't know if we looped already. 97D8. Yes. Okay, now yeah, we're through. So I think that's all. Now the next question is whether we can figure out where the patterns are stored for the tiles, right? Because if we want to extract the artwork, we have to extract the tiles as well. So how are we going to figure out that? That's going to be, so we are writing that to a specific area in VRAM2 though. Let's see where we are in our registers. We can close these guys. We don't need the breakpoints anymore. So if we look at the register viewer here, well, no, not perhaps. Well, yeah, it's going to be the sprite pattern table, I think, right? That's going to be, I think, where we write out, but that's for sprites though. I need the, is it the pattern table itself then? Let's look at the tile viewer, because I need these guys, right? These patterns, and for the sprites too, of course. Yeah, that's pattern table, but that's at 0. Is that literally at 0? Yeah. I mean, it could make sense though. Let's look at the VRAM. Yeah, that could make sense. That it's literally at 0. I don't know what a tile consists of. Like it is, like a tile is 8 by 8, right? 2, 4, 6, 8, yes. So how would that be stored? Because we have 8 bytes here, but we're probably like compressing that stuff, I would have assumed. Let's see, how can we right, that's the name table for each position. That should be at, so that's at 1800. Okay, right, so if we overlay, that's 20s, and then yeah, that's exactly our thing that we decoded, right? So that we already decoded in our little routine here. But now we need to figure out right, so that's pattern 32 instead of 0. Apparently they take 32 as in hex 20 for the black space. And I assume that, so if you look at the palette, that would be, black would be 0, right? I assume, yeah, color 0. So if we go to 0 again, I have to look up how MSX stores these sprites or these styles in memory, because that's what I don't know. Of course, we can mess with that if we add some values here. Of course, we can. Okay, so we do see a change now. That's interesting. Okay, so that's an entire column. So okay, so it's 8 by 8, and we have 8 bytes per tile, right? And FF fills it with white completely. So I think the color might be determined by something else, perhaps. Let's see what 3F does. Okay, so right. The thing I'm thinking about is whether it how the multiple colors are separated, because the sprites or the tiles are multicolor, like 2-color, and these are stored separately, right? So I have to figure out where these are stored. Okay, so that's so we'll take a look at a different one. So this one has, okay, this one is separated, right? Because this contains the 3F, 7F made the rounded corner, but the red background isn't there. So I'm assuming that how many sprites do we have, or tiles do we have here? It looks like it starts repeating here. So this is the last one, 255. Okay, so 255 times 8. Nope, in decimal, please. So we have well, it's not 2048 then, of course, right? 255. Oh, did it start at 0? Yeah, pattern 0, and that's, yeah, okay, it's 256. Okay, so we have 2 kilobytes worth of first sprite. So if we go to 248, do we then affect the second thing? So that's 800 hex. Yeah. Yes. So if we now do this, I mean, I don't see anything happening here because I don't think the color is being set. So we'll mess with the second one here. Although that also has 3F, 7F though. That's also the rounded corner. So right, so if I modify this one. Okay, so no, so it's not as I assumed, that it's one after the other. Because this doesn't edit, unless it's this one though. Oh, yes, it is. Okay, so why is that the case? I don't know why. So this set of 256 tiles is repeated 2 or 3 times, right? And I don't know why that's the case. Is why they repeat that. But I mean, fine, I guess. So this is 767. So we have 768. That's also a round number, I guess. 768 over 8. Yeah. So if we do 768 times 8, we have 6144, which is 1800 hex. Okay, so does it start again at 1800 hex? Yeah, it says 20 here, but no, okay, no, because now we're in the name table. Yeah, that's the name table. So where is the second thing stored? That's the question, right? Where are the red dots stored? Unless it's... Wait, some have 3 colors too. Is that correct? Yeah, I think they only have 2 colors, right? That would make sense. I think that they can only do 2 colors. I don't know why there is gray. Did I not see one with 3 colors? Yeah, why does this have gray though? So this has gray and red and white. That's weird. Because I did assume that there were only 2 colored sprites though. And I can't find any other. Well, yeah, this one too, right? This one has, so 5, 2, 3, where are we here? Yeah, so this one has white, gray, and red, and black. Well, or just the absence of color, of course. So that could be just a simple 0. So let's look at the color table at 2000. That's here, F1. Okay, so F1. So I assume we have, oh, that's interesting. How does this work? F1. Wait, let's see if we can find something online. Because, I mean, we can figure this out, of course. Setting a palette. Okay. That's fine. We're not concerned about that yet because I think it's the default palette. Text mode, which mode are we in? Screen 2. Setting multicolor mode. I think this is it, right? So we're in screen 2. So we have 768 kinds of patterns. Okay, pattern size is 8 by 8. That's correct. Only 2 colors can be used in horizontal 8 dots. Oh, okay. So it's per per row then. Okay, sure. Okay, we've seen this. This is indeed okay, so we have 3 blocks. Okay, that's the positioning of the tiles on the screen itself. That's fine. That's screen color. So, I mean, the information is here though. So we have 255 or 256 patterns, 3 blocks of those. I mean, that makes sense, right? That is indeed 256. So I don't know why I'm not seeing the repetition here. Oh, no, it's correct. Okay, so it stops at 255 with the king here, and then another one and another one. Yeah, okay, so it's 3 times the same thing. But what I don't see is, so you have the definition of the sprite itself. That's simply per row. I do understand that. That is quite easily. Those are these 8 bytes, right? But how do you do multiple colors though? Because if we have 256 times 8 bytes, that's 2 kilobytes, right? That's like 800 hex. So if we go to 800, it starts over, but it is this sprite. It's sprite 256. Okay, let's look at a different sprite here. So pattern 19, that would be the 20th, right? So 20 times 8 is of course 160. That's A0. So that would be this one here. So if I change that to, so that was FC, FE. Okay, I'm in the wrong one. I mean, it doesn't really matter. I can just erase this. Okay, so it is the next one. Okay, sure. Okay, it was indeed 20. It is not 0. Sure. Okay, so we have that one. So then the previous one is this one. Then okay, sure. That's 3F, 7F. That's the rounded corner. Sure. E0. That's the the 3 top bits. That's correct too, I think. And then C0. Okay, wait. I need to look at that in the calculator. So let's look at E0. E0 is the top 3 bits. That's correct. C0 is the top 2 bits. Okay, so the top 2 bits. Okay, so that is just specifying the white though. Yes. So 3F, 7F, E0, C0, 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 C3, C3 is just the white part. So my question is, where is the blue part? And that's not explained here either, right? So we have simple single color. In this module, there are 3 pattern generator tables which are compatible with graphic 1. It cannot display patterns which are overlapped on the screen. Okay, then let's look at the color table then, because I must be missing something here. Because like these C0s only put the top 2 bits on, right? So for the 3 center lines there, the 2 top bits are white, but the rest... Okay, wait. Right, if we do C0, that means the 2 top bits are 1 and the other ones are 0. So if in our color definition we can specify 2 colors, one for the 1 bit and one for the 0 bit, then it does make sense. And is that the case? And colors for 0 and 1 bits of each. Oh, okay, sure. Yeah, now it makes sense. Yeah, so the size of the color table is the same as the pattern generator table, and the colors for 0 and 1 bits of each horizontal line. So is that the 2 nibbles then, or what? That might be the case though. Oh yeah, it says here pattern. Oh, okay, sure. Pattern 0 color and pattern 1 color is the top nibble and the bottom nibble. That does make sense. So how do we do interrupted? Can we do interrupted patterns? Yeah, no. It's only there's only 2 colors per row. Yeah. Yes. Okay. So if you go look at the color table, which is at 2000, and then we go to the 20th or 21st, I guess, or no, the 19th. So that's F1. So F1 would be, well, it's color F and color 1, right? So if we want to change, so F would be black and 1 would be white, right? So if we make this F4, then the white row at the top of the little pattern would turn green, would turn blue. Okay, I'm in the calculator here. So we're changing the top row of this one to blue, where the white things are. Oh, okay, other way around. So that was F1, right? So that becomes 4, 1. Yeah. So 1 is black then. Well, okay, 1 is black and 0 is also black. Or maybe it's, well, it couldn't be transparent, right? So what is the palette thing here? Oh yeah, both 1 and 0 are black. That makes sense. So it could have been F1 or F0. Okay. So we can figure out the sprite makeup and the colors, or the tile at least. So now we just have to figure out who writes this to address 0 and 2000, right? Can I put a, I don't think I can put a write breakpoint on this, but we can figure it out with a transfer to VRAM call. Yeah, condition, I don't think I can specify. It has to look at the, yeah, I don't know. Yeah, no. Doesn't matter. We will look for calls to 5C, I think it was. If you look at the BIOS call, yeah, this would be transfer, a block transfer from VRAM to from memory to VRAM, and DE has to be 0. So we have to look for all the 5Cs, and I hope we can find those easily. Yeah, so it's this one, right? So we have 6 calls, or 6 jumps to 5C. I don't know if there's other, yeah, 7 here. So for some reason, oh yeah, we have the address itself, I guess. Oh, we have 1 call to 5C and 1 jump. Okay, sure. Right, and DE, was it? Yeah, DE was a target, right? The target in VRAM was DE. That has to be 0. Of course, this is 6B46 is a function that does nothing else than calling 5C. So we'll have to look at these calls too, of course. It's not going to be that easy. That's 1800. 1800 was the name table. That's not interesting because we do not worry about where things are positioned on screen. We already know that by decoding the artwork, right? Then 3800 doesn't matter. 1B00 also doesn't really matter. 1800, that's the name table too. 3000, then 1A20 for some reason. Again, a function, or are we back at the top? Yeah, 1800. Okay, I have to look. Yeah, I think I'm back at the top. Okay, so maybe it's this function then. 6C0, of course, these could influence this value, of course. Oops. Nope. Actually, I think it will be easier to just use a debugger and see if we can trigger on. Yeah, I think that's easiest. So 5C, right? Yeah, we're gonna do this easier by just letting the thing do the work for us. So we will. Where's my disassembly here? Did I close? Yeah, I think I closed. No, I didn't. I don't know. It was here. Okay. So we can put a breakpoint here at C. What was it? CF or C5? Come on. C5, right? Yeah, 5C. Yeah, so if we put a breakpoint here, and of course this is being called constantly, but we look at DE being 0, right? Yeah, DE is 0 now, so this is one of these calls. Okay, so HL is C0, so we are putting this on the screen now, which is one of the decoded things probably, right? Yeah, so we're putting this on the screen for a length of 800 hex, which is 2 kilobytes. So this should contain our sprites or our tile makeup, I guess. But we have to see where we're coming from. So if you look in the the stack, hopefully that gives us 6B4D. Let's look at that in the code here. 6B4D. Okay, sure, we're in this function. And then the next one is 6B3E, I think. If you look at the stack, 6B3E, which is this call, yes. Of course, that's again a function. I mean, the length is 800 hex here, so that's fine. 6B3A would be the call. So 6B7C would be the next one. 6B7C. 6B7C. That's this one of here, for here, of course. Okay, here we are. So we're loading DE as 0. That's good. The length is 2 kilobytes. We have decoded something in C000. So this call is going to get us the composition of the sprites, of the tiles, I guess, in address C000, which is what we're after, right? Because we are looking for where that information is stored in the ROM. So yeah, so let's take a note of this. And then, oops, I didn't want to do that. And then 43BF. Okay, that's here. Okay, we're loading C000 in DE and we're jumping immediately. Okay, that's a bit weird, but sure. I mean, I was hoping to get just a simple hard-coded value here, but no, we are doing some complex stuff, unless HL is being filled in here. So let's stop in 6CB8, see if we can find something there. Let's continue. Of course, we have to be in the exact same spot. Well, I mean, it doesn't really matter, right? Okay. So HL is 8B97. What does this contain? 8B97. I think we're in ROM here, right? Yeah, so this could be our sprite table, or like tile ID, or not, tile composition table in the ROM. Maybe. Which would also be encoded, right? So would that mean then that if we skip this function, we see the tile table appear at C000? Because that would have to be the case, right? Okay, so we have a screen here, that's fine. I should have popped out of this function first. Which, I mean, I can try to do a pop out here. Yes. Because, yeah, we're back where we call this. And now we are loading that into VRAM, and this is our tile thing here, right? We started with 8 zeros, so 2 empty sprites. Does that make sense? If we look at our tile viewer here, yeah, so we have the 2 first ones are empty. I mean, I haven't done it yet though, so this is old data. I'm going to have it called 6B3A. Like these 3 calls will load the 3 segments into the pattern table here. So I'm going to let it do that. Actually, I'm going to force this one here to see if we get 1 pixel on the second row. So I'm going to load. Yes, it's already there. There's my pixel. Yeah. Yeah, because now it's going to appear here. If I do the second batch, now it's appearing here. And then in the last one over here. I don't know why it's in a different spot though. Is it? No, that's just my, oh, no, that's, no, it is the same spot. Of course it is. So that means that we were correct. That this position here is being decoded. 8B97 contains data, contains our sprite data that we load into the thing here. I mean, there are multiples because like we're loading different pattern tables for the game and for the menu, so we have to like load both, right? But like, the next job will be to decode the entire the decoding routine for this set of data, and that looked a bit more complex, but I mean that's fine, I guess. So let's go back to that function, right? So this is 43BF. Which ended up here, I think, right? Yeah, so (6B, 6D). Okay, so I need to remember this one for sure. So we start at 43BF, was it? Yeah, 43BF. So we're loading C0. Okay, we're jumping to C6CB8, and that does this thing here. And this is the decoding routine. Why am I? Okay, yeah, no. Okay, we're calling 43BF. Yeah, we're calling 43BF. And we are just loading C000 as a target pointer, and we're jumping to the decoding function, okay, which is 6CB8. And this we have to reverse engineer, and then the, yeah, okay, it's over here, like 8B97. That's where we were coming from, right? 8B, yeah. So this, yes. This loads 8B97, decodes it, and loads it into VRAM. Okay, so 6B6A. 6A loads the data to decode, and then decodes, and then it loads into VRAM. So where does this go? I assume until here. Okay. It doesn't, I mean, we see loops, we see rotations, we see ands. Yeah, this is going to be the decoding function because it's all going to be compressed, right? So this data, this is the uncompressed data, but this is the compressed data that has to be stored compressed in their limited space ROM. But that is going to be it for this time. Next time we'll see if we can decode this this information. Yeah, that's going to be it. I'm hungry, so thanks for watching, and hopefully I will see you next time.